Hello and welcome to Sleepy Science. What if time is not the engine of reality, but the illusion that appears when reality becomes too complex to see all at once? What if the past is not as finished as it feels, the future is not as silent as we assume, and the present moment is only a useful shortcut your mind creates so the universe can feel livable? In this journey, we'll enter the strange frontier where quantum physics makes clocks blur, histories become uncertain, cause and effect lose their simple order, and even the flow of time begins to look less like a cosmic river and more like a story built from information, gravity, memory, and measurement. These are not myths, fantasies, or time travel tricks. They are real questions from modern physics. Questions that suggest time may not sit beneath reality at all. It may emerge from entanglement. It may be shaped by lost information. It may change under gravity. It may even disappear from the deepest equations we have not yet fully understood. So if you're ready to drift into a world where the universe may not be ticking underneath everything, tap like, hit subscribe, and step into the mystery with me. Because the deeper we look into time, the more it feels like time was never the background of existence, but one of existence's most beautiful unfinished inventions. Time may not be fundamental in quantum physics. The strangest thing about time in quantum physics is not that it can slow down, bend, or behave differently near massive objects. The strangest possibility is that time may not be a basic ingredient of reality at all, but something your mind builds after deeper processes have already happened. You feel time as the most obvious thing in existence. It seems to carry you from morning to night, from childhood to adulthood, from one breath to the next. You wake up, remember yesterday, plan tomorrow, and feel the present sliding forward like a quiet river under your feet. But when physics looks very closely at the smallest parts of nature, that river becomes harder to find. Quantum physics does not treat the world like a simple movie playing frame by frame. It describes particles and fields through probabilities, possibilities, interactions, and measurements. A tiny system does not always behave like a little object moving through a clear timeline. Before it is measured, it can be described as a spread of possible outcomes, not a single finished story. And this creates a quiet problem. If reality at its deepest level is not made of definite things following definite paths, then what exactly is time flowing through? In ordinary life, time feels like the stage on which everything happens. A cup falls, breaks, and cannot unbreak. A word is spoken, heard, and remembered. A star burns, ages, and eventually dies. But in quantum theory, time often appears less like a physical substance and more like a background setting used to describe change. It is there in the equations as a kind of clock, a way to say how a quantum state evolves. But it is not usually treated like position, energy, or momentum. You can ask where a particle might be, what energy it might have, how likely an outcome is, but asking, where is time, is not the same kind of question. Time is not something you pick up, weigh, or detect directly. It is the ordering of events, the measure of change, the rhythm your brain uses to make sense of a universe that may be more deeply organized by relationships than by ticking moments. This does not mean time is fake in the simple sense. Your alarm still rings. Your body still ages. The moon still orbits Earth. Clocks still work with astonishing precision. The point is subtler and more unsettling. Something can be real in experience without being fundamental in the deepest description. Heat feels real, but at a deeper level it comes from the motion and arrangement of many particles. Sound feels real, but it comes from pressure waves moving through air. Color feels real, but it comes from how your brain interprets light. Time may be similar. It may be something that appears when many deeper pieces of reality are viewed together. A large-scale pattern rather than a basic brick. This becomes especially important when quantum physics is brought close to gravity. In Einstein's relativity, time is not universal. It can stretch and slow depending on speed and gravity. A clock near a massive object can tick differently from a clock far away. So relativity already tells you that time is not the same for everyone everywhere. But quantum physics, in its usual form, often needs a clock outside the system, a background time against which change is measured. That works well in laboratories, because the scientist, the clock, and the measuring device can be treated as outside the tiny system being studied. But what happens when the system is the whole universe? There is no outside laboratory, no cosmic wall clock hanging beyond reality, no observer standing outside existence with a stopwatch. If you try to write a quantum description of everything, time becomes deeply mysterious, because there may be nothing external for the universe to evolve in. This is one reason some approaches to quantum gravity suggest that at the deepest level, reality may be described without a flowing time at all. Not as a dead frozen universe, but as a structure where change is understood from correlations between things, not from a master clock ticking behind them. Imagine a book with every page already present, but no one forcing you to read it from left to right, except the way your mind enters the story. Or imagine a landscape where the path is not created by a moving river, but by the relationship between stones, slopes, shadows, and footsteps. From inside the landscape, movement feels undeniable. From a deeper view, what exists may be a pattern of relations, and time may be the way conscious beings experience moving through that pattern. This is why the idea is so powerful. It does not simply ask whether time is strange. It asks whether the flow you feel is a feature of the universe itself, or a feature of how beings like us process change. Your brain is built to arrange experience into before and after. It stores memories in one direction. It predicts danger, reward, hunger, and loss. It turns change into narrative because narrative helps you survive. If you hear glass shatter, you do not wonder whether the pieces came first and the cup came later. Your mind builds a direction immediately. It says, this happened, then that happened. And for daily life, that is enough. But quantum physics quietly warns us that nature may not be made of stories at its roots. The story may be what appears when uncertain possibilities become recorded, when interactions leave traces, when the world becomes stable enough for memory to form. You experience time because you are a creature of records. You remember the broken cup, not the unbroken future. You remember yesterday, not tomorrow. You carry scars, photographs, fossils, messages, wrinkles, and echoes. These records make time feel like a river moving in one direction. But if you remove the records, remove the observer, remove the large warm world of irreversible changes, the deep laws of physics become far less committed to the flowing now you feel so strongly. The present moment may not be a glowing blade cutting reality into past and future. It may be a useful shortcut created by minds that cannot hold the whole structure at once. And this is where the science becomes personal. Because if time is not fundamental, then your life is not less meaningful. It is more mysterious. Every second you feel may be the surface of something deeper. The way a wave is the surface of an ocean, whose full depth you cannot see. The fact that time may emerge does not make your grief unreal, your love unreal, or your memories unreal. It means they belong to the level of reality where experience lives. A rainbow is not fundamental either, but no one who has stood beneath one would call it meaningless. It appears when light, water, angle, and vision come together. Time may appear when change, memory, matter, and awareness come together. It may be the rainbow of existence, not a thing sitting out there by itself, but a real pattern born from relationships. And perhaps that is why it feels so intimate. You do not merely observe time. You participate in making it feel alive. Your attention stitches moments together. Your memory gives them direction. Your body turns change into aging, and your heart turns aging into urgency. Quantum physics does not hand you a simple answer. It does not say, time is definitely an illusion, and it does not let us pretend the mystery is solved. What it offers is a more careful and more beautiful uncertainty. Maybe time is not the floor beneath reality, but a path that appears when reality is walked from the inside. Maybe the universe at its deepest level is not ticking. Maybe it simply is, and the ticking begins when parts of it start comparing, changing, remembering, and wondering. So the next time you feel a minute pass slowly, or a year vanish too quickly, or a memory return with the softness of something still alive, pause for a moment. That feeling may not be proof that time is fundamental. It may be proof that you are. A being made of change, carrying records through a universe whose deepest layer may not flow at all, yet somehow through you, learns what it means to have a past, to hope for a future, and to call this fragile brightness now. A quantum clock can blur with the system. It measures. A clock seems like the one thing in an experiment that should stay outside the mystery, quietly counting while everything else becomes strange. But in quantum physics, even the clock can be pulled into the uncertainty it is trying to measure. You are used to thinking of time as something a clock simply reveals, the way a thermometer reveals temperature or a ruler reveals length. You look at the numbers, trust the ticking, and imagine the clock as a calm witness standing apart from the event. But at the quantum level, a clock is not a magical observer outside nature. It is made of physical stuff too. It has energy, motion, internal states, tiny interactions, and limits. And the moment a clock becomes small enough, delicate enough, or deeply connected enough to measure a quantum system, it can no longer remain perfectly separate from what it measures. The clock and the system can become linked, and once they are linked, the clean idea of the system changed at exactly this time begins to soften. This is what it means to say that a quantum clock can blur with the system it measures. It does not mean the clock becomes imaginary, or that time turns into a fantasy, or that scientists can no longer measure anything. It means the old picture of a perfect clock watching from the outside breaks down. A quantum clock must interact with the thing it times. An interaction is never completely innocent in quantum physics. If you want a clock to tell you when something happened, something about the clock must change when the event occurs. A particle must affect it. A signal must reach it. A state must be recorded. But that record does not appear for free. The act of recording can disturb the system, and the clock itself may become entangled with the event, meaning the clock's reading and the system's condition are no longer two fully independent facts. They become parts of one combined situation. Think of trying to measure the exact moment a soap bubble changes shape by touching it with your finger. The touch gives you information, but it also changes the bubble. In quantum physics, the problem is even deeper, because the touch may be incredibly small, and yet it still matters. A quantum clock might be built from atoms, spins, light pulses, or other tiny systems whose states shift in regular ways. These shifts can act like a hand moving across a clock face. But unlike the bold hands of a wall clock, a quantum clock's hand can itself be uncertain. It may not point to one perfectly sharp time. It may have a spread of possible readings. And if it is used to time another quantum object, the object's possible changes and the clock's possible readings can become woven together. The result is not a single clean sentence like, "This happened at this exact instant," but a more careful statement. When the clock shows something like this, the system is likely to be in something like that state. This is a softer, relational kind of timing, where time is not simply stamped onto reality from outside, but inferred through physical correlations inside the experiment. This matters because many ordinary explanations of quantum physics quietly assume a perfect classical clock in the background. The clock is treated as stable, external, and definite. In real laboratories, this is usually good enough because the clocks are large, carefully controlled, and far less fragile than the microscopic systems being studied. But if you ask the deeper question, what if the clock itself must obey quantum rules? Then the boundary between the timekeeper and the thing being timed becomes less clean. The clock is no longer just an instrument. It becomes part of the quantum description, and that changes the meaning of measurement. Suppose you are watching a tiny quantum system that can change from one state to another. To know when the change happens, you need a clock coupled to it. But if the coupling is too weak, the clock barely learns anything. If the coupling is too strong, the clock may disturb the system too much. The more information you demand, the more carefully you must face the cost of getting it. This is not because nature is hiding the answer in a dramatic way. It is because information is physical. A record must be carried by something. A clock reading must be stored in matter or light. And in quantum physics, storage, interaction, and disturbance belong to the same world. There is no completely ghost-like measurement that leaves no trace and causes no effect. Even the best quantum clock must be a participant. This idea becomes especially strange when you stop imagining the clock as a machine on a table and start imagining it as one quantum system measuring another. Then the clock does not simply say what time it is, it shares a state with what it measures. Its tick is not separate from the event, it is part of the event's physical story. The clock's reading may become clearer only because the system's possibilities have narrowed, or the system's description may depend on which clock reading is considered. In that sense, timing is not just a label placed on change. It is a relationship between two changing things. One system becomes the reference, the other becomes the measured process, and the meaning of when is built from their correlation. This is why quantum clocks feel so unsettling. They remind you that even measurement tools are not outside the universe. There is no perfect eye floating above reality, no flawless metronome beyond matter, no final watch that ticks without being touched by anything. Every clock is a physical object trying to describe other physical objects. And at the smallest scales, that description can become blurred by the very connection that makes it possible. Yet this does not weaken science. It makes it more honest. It teaches that precision is not magic. It is an achievement. It is something built carefully from noisy, fragile physical parts. And maybe this is why the idea feels quietly human. You also measure your life with inner clocks: memory, expectation, heartbeat, waiting, attention. When you are calm, time opens. When you are afraid, time tightens. When you are deeply absorbed, hours disappear. Your personal clock is not separate from what you experience either. It blurs with the system it measures, and the system is your life. Quantum physics does not prove that human time and quantum time are the same thing, but it gives you a humbler image of measurement itself. To measure is not to stand apart untouched. To measure is to enter a relationship. The clock changes with the event. The observer changes with the act of observing, and knowledge arrives not as a pure spotlight, but as a trace left by contact. So when you imagine a quantum clock, do not picture a perfect golden mechanism ticking in empty space. Picture something more delicate, a tiny rhythm trying to mark another tiny rhythm, each one influencing the other, each one becoming meaningful only through the link between them. And perhaps that is the deeper lesson hidden in the blur. Time is not always a command shouted from outside reality. Sometimes it is a whisper exchanged between systems, a fragile agreement between what changes and what keeps count, a quiet reminder that even the act of knowing when something happens is itself something that happens. The future and past may be more symmetric than they feel. You feel the past behind you like a locked room and the future ahead of you like a dark hallway. But the deeper laws of physics may not divide them as sharply as your mind does. In ordinary life, the difference seems undeniable. Yesterday has already happened. Tomorrow has not. A broken glass does not rise back onto the table. Smoke does not fold itself neatly into a candle flame. And the words you speak cannot be unsaid once they enter another person's memory. Your body is built around this direction. Your brain stores traces of what came before, not what comes after. Your skin carries scars from old moments, not future ones. So it feels natural to believe that the past is solid and the future is open. But when physicists look beneath the warm, messy world of daily experience, they find something quietly unsettling. Many of the basic equations that describe particles do not strongly care which direction time is running. If you could watch a simple microscopic interaction, stripped of heat, friction, memory damage, and all the large-scale clutter of life, the laws often allow the sequence to be reversed without breaking the rules. A particle can scatter, a wave can spread, a quantum state can evolve, and in many ideal cases the same description can be run backward. It is not that scientists think your coffee will spontaneously unmix from the milk, or that your childhood is waiting to replay itself in reverse. The point is more delicate. At the deepest level, nature often seems less committed to the emotional arrow of time than we are. The past and future may be more symmetric in the machinery of physics, while feeling profoundly asymmetric inside conscious experience. This is one of the quiet shocks of modern science. The world you live in has a direction, but the rules underneath it are often closer to a two-way road than a one-way street. The strongest reason you feel time moving forward is not simply because the basic laws demand it at every level, but because the universe began in a very special, highly ordered condition. And since then, disorder has generally increased. This is the idea behind the arrow of time. If you drop a drop of ink into water, it spreads. The spreading is easy because there are many ways for ink and water to become mixed, and very few ways for them to remain neatly separated. The reverse is not forbidden in the most absolute logical sense. It is just unimaginably unlikely. You never see the ink gather itself back into a perfect drop because the number of microscopic arrangements required for that reversal is so tiny compared with the number of arrangements that look mixed. This is where the feeling of past and future begins to emerge. The past is the direction where there were fewer possible arrangements, fewer records, less spreading, less scrambling. The future is the direction where possibilities multiply, traces accumulate, and information becomes harder to gather back into its original form. Your memory works because the past left marks. A footprint in sand, a fossil in stone, a photograph, a scar, a sound recorded in air, and then in a device, a pattern stored in your nervous system. These records all point in one direction, because making a record is itself a physical process that usually increases disorder somewhere. To remember is not just to hold an image. It is to live inside a universe where traces can be formed and preserved. That is why you remember the glass before it broke, but not the exact future shape of the shards before they fall. The asymmetry you feel is built from records, and records are built from irreversible processes. Yet quantum physics complicates this picture in a beautiful way. A quantum state, when left alone and perfectly isolated, can often evolve in a way that preserves information. In principle, the earlier state can be reconstructed from the later one. This does not mean the world is easy to reverse in practice. Real systems are never perfectly isolated. They leak information into their surroundings. They interact with air, light, heat, measuring devices, and other particles. Once that happens, the clean reversibility becomes hidden inside an enormous web of correlations. The information may not be destroyed in the simple sense, but it becomes so widely spread that no ordinary observer could gather it back. It is like tearing a poem into dust and scattering it across the atmosphere. Maybe every fragment still exists somewhere, but the poem is gone for anyone who lives at human scale. This is why the future feels open while the past feels fixed. The past has left stable traces. The future has not yet left them for you. But from a deeper physical view, the distinction may be less absolute than your experience suggests. Some interpretations and approaches in quantum theory even explore the idea that both past and future conditions can help describe a quantum system, as if reality is not only pushed from behind by causes, but also constrained by the way it is eventually measured. This does not mean you can send messages to yesterday, and it does not prove destiny is written in advance. It simply shows that the usual human picture of time as a single line of causes marching forward may be too simple for the quantum world. The equations can sometimes be read with a surprising neutrality, where what comes before and what comes after are part of one complete description rather than two separate kingdoms. Even in particle physics, there are deep symmetry ideas suggesting that nature has hidden balances between matter and antimatter, left and right, forward and backward. These symmetries are not perfect in every ordinary sense, and scientists have found important exceptions in certain particle processes. But the fact that such symmetry plays a central role at all is revealing. It tells us that the universe is not built entirely around our feeling of before and after. Our experience of time is local, biological, thermodynamic, and memory-based. The underlying laws may be calmer, colder, and more balanced than the story our minds tell. And maybe this is why thinking about time symmetry feels both scientific and strangely personal. You cannot return to the past, but the past is not a glowing object stored somewhere behind you. It is a pattern of traces in the present. You cannot see the future, but the future is not pure nothingness either. It is the range of ways the present can continue. You live between these two illusions, the past as permanently solid, the future as completely empty. Physics softens both. It says the past is known because it has records, and the future is unknown because its records have not formed for you yet. It says the direction of time may arise not from a cosmic command, but from probability, information, and the special history of the universe. And this does not make your life colder. It makes each moment more fragile and more luminous. Every choice you make becomes part of the record-making machinery of reality. Every word, every touch, every small act leaves traces that help define what will later be called the past. The future may be physically less alien to the past than it feels, but emotionally, ethically, humanly, it is still where your responsibility lives. So when you sense time pulling you forward, remember that you are not simply being carried by a river. You are watching symmetry break into experience. You are living in the place where reversible laws become irreversible memories, where quiet equations become aging faces, where possibility becomes history one trace at a time. And perhaps the deepest mystery is not that the past is gone, or that the future is coming, but that a universe whose foundations may be nearly balanced between both directions can still give rise to you. A creature who remembers one side, hopes toward the other, and calls the narrow flame between them now. Some quantum equations don't need a flowing time. Somewhere at the edge of modern physics, there are equations that describe a universe without ever asking it to move from one second to the next. That sounds almost impossible, because everything about your life seems to depend on flow. A breath begins and ends, a thought appears and fades, a shadow crosses a wall, a star burns through its fuel, and your own reflection changes slowly enough that you only notice it when an old photograph surprises you. You are used to imagining physics as a story engine, a set of rules that takes the world as it is now and tells it how to become the world a moment later. Many familiar equations work exactly like that. They need a clock in the background. They say, in effect, give me the present, give me the passing of time, and I will tell you how the system changes. But some of the most important ideas in quantum theory and quantum gravity point toward a stranger possibility. Certain descriptions of reality do not require a flowing time at all. They do not begin with a cosmic stopwatch. They do not picture the universe as a film being pulled through a projector. Instead, they describe relationships, allowed states, constraints, and patterns that simply have to fit together. The change you experience may then emerge from inside those patterns, rather than being poured onto them from outside. One of the most famous examples appears in attempts to combine quantum physics with general relativity, where gravity is not treated as a force moving through space, but as the shape of space-time itself. In ordinary quantum physics, time usually stands outside the system like a quiet reference line. But in general relativity, time is part of the system. It bends with gravity. It depends on where you are and how you move. So, when physicists try to describe the entire universe quantum mechanically, they face a strange problem. If the universe includes everything, then there is no outside clock left to measure it against. You cannot step beyond all of existence and say, now the universe has advanced one tick. There is no external balcony, no universal metronome, no master observer holding time apart from reality. This is where so-called timeless approaches become so fascinating. A famous equation connected to quantum gravity, often discussed under the name Wheeler-de Witt, does not work like a normal equation of motion with a clear flowing time. Instead of saying, here is how the universe changes from one instant to the next, it gives something more like a total condition the universe must satisfy. To many physicists, this creates what is sometimes called the problem of time. The universe seems full of change, yet the deepest attempted description can look frozen. But frozen does not necessarily mean dead. Think of a musical score printed on paper. Nothing on the page is moving, and yet the music is there in a different form. The melody appears when a musician reads the relationships between notes. Or think of a map. The map itself does not walk, but it contains distances, paths, and possible journeys. In a similar way, a timeless quantum equation may contain the structure from which experience change can arise, even if the equation itself does not contain a simple river of time. The key idea is that before and after might not be basic labels written into the foundation. They may be reconstructed from correlations. One part of the universe can act like a reference for another part. A physical process can serve as a clock, not because time flows outside everything, but because one changing system can be compared with another. You do not need the universe to move through an external time if you can say, when this part has this condition, that part has that condition. This is subtle, but powerful. It turns time from an invisible container into a relationship between physical things. Instead of imagining the whole universe marching forward under a cosmic command, you imagine different parts of reality defining order for one another. A pendulum tells time because its swing is compared with other events. An atomic clock tells time because regular transitions inside atoms are compared with the world around them. But if you describe everything at once, the clock is no longer outside the picture, it is just another part of the pattern. This is why timeless equations do not erase experience. They challenge where experience comes from. They ask whether flow is fundamental or whether it is what appears when beings inside the universe track correlations, form memories, and arrange events into a usable order. In some quantum systems, even without invoking the whole universe, physicists already work with states that do not obviously flow in the everyday sense. Certain stable quantum states can have properties that remain unchanged over time, even though something deeper is still being described. An atom in a stable energy state is not like a tiny planet visibly orbiting in a little loop. It is described by a pattern of possibility that can remain steady until interaction changes what can be known about it. This helps loosen the ordinary picture. Nature is not always a little machine visibly progressing frame by frame. Sometimes it is better described as a set of allowed patterns. And what we call change appears when patterns interact, compare, or become recorded. The danger is to turn this into a false dramatic claim, as if science has proven time does not exist at all. It has not. Clocks work, experiments depend on timing. Your body ages, signals arrive in order. What physics has shown is more careful and more interesting. The role of time is not the same in every theory, and at the deepest frontier, time may not be a simple background flow. It may be something that has to be explained, not something we are allowed to assume. And that shift is enormous. It is like discovering that the stage beneath every actor might itself be made of relationships between the actors. The stage is still useful. The play still happens, but the foundation is not what it seemed. For you, sitting inside this flowing life, the idea can feel almost silent at first, then slowly unsettling. If some quantum equations do not need flowing time, then the feeling of time passing may be less like a universal heartbeat and more like a perspective from within the pattern. You are not outside the music reading the whole score at once. You are one note becoming aware of the next. You are one small region of reality, carrying memory, expectation, and attention, stitching a path through a structure too large to hold in a single thought. And perhaps that is why the present feels so precious. Not because it is a sharp physical knife slicing the universe into pieces, but because it is how a conscious creature experiences correlation from the inside. The universe may not need a flowing time in its deepest grammar, yet you need flow to live, to learn, to forgive, to hope. The timeless equation and the human heartbeat are not enemies. They are different levels of description. One may describe the whole pattern in a calm, almost motionless way. The other feels the pattern as a journey. So when you hear that some quantum equations do not need flowing time, do not imagine a blank universe where nothing happens. Imagine instead a reality so deep that motion may be an internal reading of structure. A world where clocks are not rulers of existence but participants inside it, and where your sense of moving forward is not a simple illusion, but a local truth born from a greater stillness. Maybe the universe at its foundation is not rushing anywhere. Maybe rushing is what it feels like when a small part of the universe wakes up. remembers, compares, and begins to call the next relation future. A particle's history can be less definite than its result. A particle can arrive with a clear answer while refusing to give you a clear story of how it got there. That may be one of the most quietly difficult ideas in quantum physics, because your mind naturally wants every result to have a path behind it. If a stone lands in the grass, you assume it flew through the air along some route. If a car appears at the end of a road, you assume it drove along a sequence of places. If a message reaches your phone, you believe it traveled through a chain of signals. Ordinary life teaches you that every final state has a definite history, even when you did not witness it. The history may be unknown to you, but you assume it exists. Quantum physics forces a more careful possibility. For a tiny particle, the final result can be definite, measurable, and real, while the route that led to it may not be a hidden classical path waiting to be discovered. The particle may hit a detector at one exact spot, leaving a small mark, a click, a record, something scientists can write down and compare. But before that click, if no measurement forced a specific route into existence, the particle's history may not be a single finished line. It may be a blend of alternatives, a set of possibilities that do not behave like ordinary missing information. This is not just because we are ignorant. It is not like losing sight of a bird behind a tree and saying, "I do not know which way it flew." In many quantum experiments, nature acts as if the unobserved alternatives remain active together, combining and interfering before the final result appears. The outcome is sharp, but the path is not. A simple way to see this is to think of an experiment where a particle has two possible routes toward a detector. If you do not check which route it takes, the final pattern can show interference, meaning the possibilities have combined like overlapping ripples. If you do check, the interference disappears and the particle behaves more like it had one route. The lesson is not that the particle secretly chose a normal path and we failed to see it. The lesson is that asking for a path can change the kind of experiment you are doing. The question, "Which way did it go?" is not always a harmless question. It can create a different physical situation, one where alternatives that once worked together are now separated into records. This is why quantum history is less like a trail of footprints and more like a story written only where the world leaves marks. Between preparation and measurement, you cannot always fill in the blanks with a tiny classical movie. The particle was not necessarily really here, then really there, then really over there, in the way a dust speck might be. Quantum theory gives you reliable rules for predicting the final result, but it often refuses to provide the kind of hidden travel diary your intuition wants. And that refusal is not a weakness of the theory, it is one of its deepest lessons. The world does not owe us a familiar story between observations. It owes us patterns that can be tested, and quantum physics has been extraordinarily successful at predicting those patterns. This becomes even stranger when scientists try to reconstruct what happened after the fact. In ordinary reasoning, the result should help reveal the history. If you find muddy shoes by the door, you infer someone walked through mud. If you see smoke, you infer fire. But with quantum systems, different possible histories can lead to the same result, and sometimes those histories cannot all be treated as real at the same time. Some approaches, such as the consistent histories framework, try to describe quantum events using sets of possible histories, but even there, the histories must be chosen carefully so they do not contradict the interference structure of the system. You cannot always combine every possible story into one grand classical account. Some questions can be meaningful in one experimental context and meaningless in another. This is deeply uncomfortable because it means the past of a quantum particle is not always a simple object you can uncover. It can depend on which records exist, which measurements were made, and which framework can be used without contradiction. The result may stand firm, but the "what really happened before" may have no single classical answer. This is one reason quantum physics feels so different from ordinary uncertainty. If you shuffle cards and draw one, the card had a definite identity before you looked. You simply did not know it. But in quantum physics, before measurement, the system may not have possessed the definite property you later observe. The act of measurement does not merely reveal a pre-written label in every case. It helps define which property becomes part of reality's record. That does not mean human consciousness magically invents the world. The measuring device, the environment, and physical interaction are enough to create records. What matters is that a trace is made. Once the trace exists, the result becomes part of the world's stable memory. Before that, the system may be described by a spread of possible histories, and those histories can overlap in ways no ordinary object ever does. This idea also teaches a valuable discipline. Not every question that feels natural is physically well defined. Where was the particle before it was detected? Sounds simple, but nature may answer, that depends on how you try to know. The final dot on the detector is real. The statistics across many dots are real. The experimental arrangement is real, but the imagined little route connecting them may be something your mind adds, because it is trained by daily life, not something the quantum world guarantees. And perhaps this is where the science becomes quietly philosophical without becoming false. You too often want your life to have a clean line behind every outcome. You want every feeling, mistake, turning point, and arrival to have one clear cause, one path, one explanation that makes the result feel inevitable. But sometimes the truth is more layered. Many possibilities shape the moment. Many almost events, pressures, choices, and conditions overlapped before one result became visible. Quantum physics does not prove that human life works like a particle, and we should not pretend it does. But it does offer a humbling metaphor grounded in real science. An outcome can be definite without its history being simple. A thing can arrive without having traveled like a tiny ball through a tiny corridor. Reality can give you a mark before it gives you a story. So when you imagine a particle appearing on a screen, do not picture a miniature object hiding its route from you like a secret. Picture something stranger and more precise. A final fact emerging from a field of possible histories, some reinforcing one another, some cancelling one another, until the world leaves one record behind. The detector says, it ended here. But the silence before that ending may not contain a single path. It may contain the deep quantum truth that becoming definite is not the same as having always been definite, and that sometimes the universe does not move from story to result, but from possibility to record, leaving us to learn that reality is not always less real when its history is unclear. Cause and effect can become hard to order. Cause and effect feel like the bones of reality until quantum physics asks you to name which bone came first, and the answer begins to dissolve. In everyday life, the order seems obvious. The match strikes, then the flame appears. The hand pushes, then the door opens. The storm gathers, then the rain falls. Your mind is built to trust this sequence so deeply that you rarely notice it working. You do not simply see events, you arrange them into causes and consequences. This arrangement gives the world its sanity. It lets you learn from pain, plan for tomorrow, repair mistakes, and believe that actions matter. But when physics moves into the quantum world, especially into situations where tiny systems can remain in multiple possible conditions until interactions create a definite record, the old chain of first this then that becomes harder to hold. The problem is not that cause and effect disappear completely. Science still depends on patterns, influence, preparation, measurement, and prediction. The problem is that the order of influences may not always fit the simple picture your daily life teaches you. In the classical world, you imagine events lined up like beads on a string. One bead touches the next touches the next, and a story forms. In quantum physics, the beads can be less like solid objects and more like possibilities that only become fixed when the experimental setup forces a particular kind of answer. When two events are deeply connected through a quantum system, asking which one caused which may not always have the same clean meaning it has when one billiard ball hits another. Sometimes the result is not best described as one event pushing another in a familiar direction, but as a whole arrangement producing correlations that cannot be broken into a neat sequence without losing what made the experiment quantum in the first place. This is where the mystery becomes both real and careful. Physicists do not simply say, anything can cause anything, or the future magically controls the past. in a loose, dramatic way. They ask a sharper question. Can every quantum process be explained as events happening in a definite causal order, even if that order is hidden from us? In many cases, yes. But in some advanced theoretical and experimental work, researchers have explored situations where the order of operations can itself behave in a quantum-like way, not fixed as only one sequence from the start. In such cases, it may be too simple to say that operation A happened before operation B, or B happened before A, as if nature secretly chose one ordinary timeline and merely concealed it. The deeper description can involve an order that is not classically definite. This does not mean you can break causality in daily life. You cannot receive a reply before sending the message, or eat dinner because you will be hungry tomorrow. Large objects, warm environments, and ordinary records quickly settle into stable orders. But at the delicate quantum level, before the world becomes heavy with traces, the arrangement of influence can become more subtle than a straight arrow. To understand why, think about how much of cause and effect depends on records. You know the vase fell because there are shards on the floor, a sound in memory, maybe a video, maybe a guilty cat leaving the room. The order is written into the environment, but quantum systems can be isolated enough that the environment has not yet carved the story into stable marks. Without those marks, some questions about sequence can become less like discovering a hidden fact and more like choosing a framework that lets you describe what can be meaningfully known. The cause is not always a little spark traveling from one tiny object to another. Sometimes, the cause is the entire experimental arrangement, how the system was prepared, what it interacted with, what kind of measurement was made, and what correlations appeared at the end. That is a different kind of explanation, less like a row of falling dominoes and more like a musical chord where the notes make sense together but cannot always be understood as one note causing the next. This challenges something very old inside human thinking. We want reality to be a detective story. We want every outcome to have one culprit, every event to have one origin, every strange result to lead backward to a single clear trigger. Quantum physics does not always give that comfort. It teaches that the world can be lawful without being narratively simple. A laboratory result can be predictable in its statistics, repeatable in its pattern, and still resist being turned into a tiny classical drama of this happened, then this happened, therefore that happened. And this is not a failure of imagination. It is a warning against using the wrong kind of imagination. If you try to force the quantum world into the shape of everyday objects, you may create a story that feels satisfying but teaches the wrong lesson. The real lesson is more unsettling and more beautiful. Causality may be a structure that becomes clear when interactions leave stable records, not a simple chain that exists in the same way at every depth of reality. At the level of your life, cause and effect remain essential. Kindness can change someone's day. Neglect can damage trust. Practice can build skill. Choices have consequences. But physics whispers that underneath this human clarity, nature may be less like a line and more like a web, where influence can be distributed through a whole setup before it becomes a finished sequence. And maybe that is why the idea lingers in the mind. You begin by asking how a quantum event can have an unclear order, but you end by wondering how many of your own explanations are just clean stories placed over tangled origins. How often do you say, this caused that, because your mind needs a handle, when the truth was a network of timing, context, memory, pressure, chance, and response? Quantum physics does not erase responsibility, but it humbles certainty. It reminds you that the universe may not always speak in the grammar of before and after. Sometimes it speaks in correlations. Sometimes it gives you a pattern before it gives you a sequence. Sometimes the question is not which event came first, but what whole arrangement made this outcome possible? And as you sit with that, cause and effect do not become meaningless. They become deeper, less like a chain dragging reality forward, and more like a hidden architecture of relationships, quietly deciding when the world can become a story at all. Quantum systems can evolve without a clear storyline. A quantum system can change with perfect mathematical discipline while refusing to turn itself into the kind of story your mind knows how to follow. In everyday life, change feels narrative. A seed becomes a sprout becomes a tree, a cloud gathers, rain falls, a child learns a word, then another, then slowly becomes someone with a history. You understand the world by linking scenes together. This happened, so that followed. This object moved here, then there. This process began, developed, and ended. But quantum systems often evolve in a way that is deeply lawful without being story-like. A small quantum system, left alone, does not need to behave like a tiny character moving through a sequence of definite scenes. It can be described by a changing state of possibilities, where different potential outcomes develop together, overlap, rotate, strengthen, weaken, and prepare the probabilities for what might later be observed. The evolution can be smooth and precise, yet if you try to translate it into ordinary language, it slips away. You want to say, the electron went from this place to that place, or the atom decided this, then became that. But the theory often gives you something less familiar and more honest, a complete rule for how the system's possibilities change, not a clear little movie of what the system was doing between observations. This distinction matters. Quantum evolution is not chaos. It is not random in the lazy sense. Before measurement, the quantum state can develop according to strict rules, and scientists can use those rules to predict experimental patterns with astonishing accuracy. What is unclear is not whether the system evolves, but whether that evolution can be translated into a classical storyline. Imagine listening to a song not as a melody played one note at a time, but as a changing cloud of tones, where future harmonies are already shaping the tension of the present, and where the final note you hear is only one expression of a deeper structure that was never simply a sequence of footsteps. That is closer to the feeling of quantum evolution. It is structured but not always narrative. In a laboratory, this shows up in many ways. An atom can be placed in a superposition of energy states, and while nothing visible seems to be happening, the relationships between those possible states can change. Their phases shift, meaning the internal timing between possibilities changes, and this can affect what is later measured. A quantum bit in a computer can evolve through controlled operations, not as a miniature switch simply flipping from 0 to 1, but as a delicate balance of possibilities that can be guided, combined, and then read out. A photon moving through an interferometer may not offer a simple travel tale, yet the changing relationships between its possible alternatives determine whether light appears at one detector or another. In all these cases, the system has evolved, but the evolution is not a diary. It is more like a recipe written in probabilities and relationships. The ingredients are not definite events. They are potential outcomes arranged in a way that can later become a definite result. And when measurement finally happens, the story seems to snap into focus. A detector clicks. A value is recorded. A screen shows a mark. Suddenly, your mind wants to backfill the missing narrative. It wants to say, "Ah, so that is what was happening all along." But quantum physics asks you to be careful. The final result does not always license a simple past tense story. The system may have evolved as a whole field of possibilities, and the measurement selected one outcome from that structure. The storyline is often something we add afterward, because human understanding is uncomfortable with naked pattern. We are creatures of plot. We want actors, motives, journeys, and endings. Quantum systems give us preparation, evolution, interaction, probability, and record. They give us science, but not always a tale. This is why quantum physics can feel colder than myth and more mysterious than myth at the same time. It removes the familiar characters, but it reveals a deeper kind of order underneath them. A quantum system can remain coherent, meaning its possibilities stay connected in a way that allows them to influence one another. Coherence is fragile. The moment the system interacts too strongly with its surroundings, the delicate possibility structure leaks into the environment, and the world begins to look classical again. That leaking process is one reason ordinary objects seem to have clear histories. Your chair, your hand, your coffee cup, your room. They are constantly interacting with air, light, heat, and everything around them, so their quantum possibilities are not preserved in any usable way. They become locked into stable appearances. They gain a storyline because the environment is continuously recording them. But an isolated quantum system can stay in a more subtle condition for a while, evolving without becoming a sequence of public facts. It changes, yet it does not confess that change in the language of everyday events. This teaches something real and important. A clear storyline may be a feature of large, recorded, environment-saturated reality, not a guarantee at every level of nature. At the quantum level, what exists between preparation and result may be better understood as evolving information about possibilities, not as a hidden miniature drama. And this does not make the world less real. It makes reality less dependent on the shapes our minds prefer. You are used to thinking that understanding means turning something into a story. But physics shows that understanding can also mean accepting a pattern that cannot be fully pictured, only carefully described and tested. That is a hard lesson, because it asks you to trust clarity without imagery, precision without a familiar scene. And maybe that is where the idea becomes quietly reflective. Your own life feels like a story because memory edits it that way. You remember beginnings, crises, turning points, conclusions, but even inside you, much of what changes has no clean storyline. Cells repair themselves. Thoughts form before they become words. Emotions rise from hidden layers of body and brain. Decisions gather from pressures you never fully see. You are not a quantum system in the simple laboratory sense, and we should not pretend human life follows quantum rules in a poetic shortcut. But quantum physics reminds you that reality can be meaningful before it becomes narratable. Something can evolve before it becomes explainable. Something can be lawful before it becomes imaginable. So when you think of a quantum system evolving without a clear storyline, picture not confusion, but a deeper kind of order, a silent transformation beneath the surface of events, a disciplined movement of possibilities, a reality preparing outcomes without acting out a simple plot for your mind. The universe does not always tell stories at its roots. Sometimes it composes patterns, and only later, when a record appears and a mind looks back, do we gather the fragments, smooth the edges, and call it what happened. The arrow of time may come from lost information. The arrow of time may not be drawn by a cosmic clock, but by all the information the universe keeps spreading beyond your reach. You feel time moving forward because things become harder to undo, harder to reconstruct, harder to return to their earlier shape. A clean table becomes cluttered, a hot drink cools into the room, a scent released in one corner slowly fills the air, and a shuffled deck does not casually arrange itself back into perfect order. These events feel ordinary, almost too familiar to notice, but hidden inside them is one of the deepest clues about why time has a direction. The world does not simply move forward because seconds are passing. It moves forward in the way you experience it, because information about the exact earlier state becomes dispersed into more and more places. When a cup of hot tea cools down, the heat has not vanished into nothing. Energy has moved into the surrounding air, the cup, the table, tiny motions of countless molecules. But the exact details of where that energy went become so widely spread and so impossibly complicated that no ordinary observer could gather them back. The original order has not been destroyed in a simple dramatic sense. It has become inaccessible. This is what entropy is often about at a deeper level. Not just mess, but the number of hidden microscopic arrangements that could produce the same visible situation. When something has low entropy, you know more about its structure. Its possibilities are narrower. When entropy grows, there are more ways the unseen details could be arranged, and your knowledge of the exact microstate becomes poorer. A freshly stacked deck tells you a lot. Every card is in a known place. A thoroughly shuffled deck still has every card, but the precise order has become one among countless possibilities. Nothing mystical happened. The information did not turn into smoke. It became difficult to access, difficult to reverse, difficult to compress into a simple description. That difficulty is what you feel as the direction of time. In classical daily life, this seems obvious because large systems have enormous numbers of parts. Air molecules, photons, vibrations, heat, surfaces, tiny impacts, and environmental traces all carry fragments of information away. Once those fragments scatter, reversing the whole process would require control over almost everything involved. To make the perfume return to the bottle, you would need to know the position and motion of an absurd number of molecules and gently guide them back. To make a cool drink warm itself by pulling heat only from the room in exactly the right way, the surrounding particles would need to coordinate in an unbelievably specific pattern. The laws of physics may not forbid such a reversal in the most ideal microscopic sense, but the odds are so extreme that for the universe we live in, it becomes effectively impossible. This is where the arrow of time appears, not as a command written above reality, but as a statistical fact born from how information spreads. Quantum physics adds another layer. In a perfectly isolated quantum system, information is generally thought to be preserved in the full state of the system. The deep evolution is not supposed to simply erase details. But real systems do not stay perfectly isolated. They interact with their surroundings. A particle bumps into a field. An atom emits light. A measuring device records a result. A room absorbs heat. Each interaction can entangle the system with the environment, meaning information about the system becomes shared across many degrees of freedom. From the limited perspective of someone inside the world, it looks as if information has been lost, because you no longer have access to the complete web of correlations. This is important. The lost information that gives time its arrow may often mean lost to practical observation, lost into the environment, lost from the small part of the world you can track. Not necessarily annihilated from the universe as a whole. The distinction matters because it keeps the science honest. The universe may keep an unimaginably detailed account in its full physical state, while every local observer experiences a growing blindness. And that blindness becomes time. You remember the morning not because the past is stored in some glowing cosmic archive, but because records of it exist now, patterns in your brain, messages on a phone, light reflected into photographs, slight changes in objects and bodies. But those records are incomplete. They are summaries, compressed traces, not the full event. Every moment leaves marks, and every mark also leaves out almost everything. The deeper details spread into the air, the walls, the warmth of a room, the microscopic world you cannot inspect. So the past feels fixed, because it has left partial records, while the future feels open, because its records have not yet formed. Your sense of time is built from this imbalance. Traces behind you, uncertainty ahead of you, and information constantly leaking from the knowable into the almost unknowable. This also explains why the universe's beginning matters so much. For time to have an arrow, the early universe must have been in a very special low entropy condition. If it had begun already maximally scrambled, there would be no strong direction for entropy to increase, no clear slope for time to roll down. The mystery is not only why things become disordered, but why they ever started ordered enough for disorder to have a direction. That question remains one of the profound puzzles in cosmology and physics. It sits quietly underneath every clock, every memory, every aging face. The flow you feel may be the universe moving away from an unusually ordered beginning, with information spreading, correlations multiplying, and recoverable detail becoming more and more hidden. And still, there is something strangely gentle in this. You are not just living through time, you are living through the loss of perfect access. Every second becomes a trade. The world gains new traces, but loses simplicity. You gain memories, but lose the exact fullness of the moment that made them. A conversation becomes a feeling becomes a memory becomes a faint outline you carry forward. Time from this view is not only passage, it is compression. It is the universe turning exactness into records, and records into stories, and stories into the fragile sense that you have been moving all along. So, when you feel a day slipping away, it is not simply disappearing. Its information is spreading into you, into your surroundings, into countless tiny changes no one will ever fully gather again. The arrow of time may be made from that spreading. The quiet transformation of clear order into hidden detail, of present experience into incomplete trace, of the fully lived moment into something the universe still holds somewhere, but that you can only remember as a softened echo. The present moment may be a classical shortcut. The present moment feels like the only place reality is truly alive. Yet physics may treat it more like a useful shortcut than a fundamental slice of the universe. You feel now with such intimacy that it seems impossible to doubt. This word, this breath, this sound in your ears, this small pressure of your body against the chair, all of it appears to gather into one glowing point called the present. The past seems gone, the future seems not yet here, and the present feels like the thin, sharp edge where existence actually happens. But that feeling may be less a direct view of reality, and more a simplified interface your brain and classical experience create, so you can live inside an overwhelming universe without being lost in its full complexity. In classical physics, the present has a very convenient role. If you know the exact state of a system right now, such as where everything is and how it is moving, then in principle you can calculate what comes next. The now becomes a kind of snapshot, a clean frame of reality from which the future unfolds. This works beautifully for falling stones, orbiting planets, swinging pendulums, and many everyday objects. It is the world of clear positions, definite velocities, stable objects, and smooth prediction. But quantum physics makes that picture harder to defend at the deepest level. A quantum system is not always a set of definite properties sitting neatly inside a single present frame. Some properties may be undefined until measured. Some possibilities may coexist in the description. Some outcomes can only be predicted as probabilities. So when you say, what is the exact present state of this tiny system? Nature may not hand you a complete classical inventory. It may give you a quantum state, which is not the same as a list of finished facts. It tells you what can be known, what can happen, and how likely different outcomes are. But it does not always provide the familiar solid now your senses expect. The present, then, may be a shortcut that becomes reliable only when reality is large, warm, noisy, and constantly interacting with its surroundings. A chair seems to have a definite present because countless interactions with light, air, heat, and the room are continually stabilizing its appearance. The environment is, in a sense, always checking it, always spreading information about it, always making it behave like a classical object. You do not see a chair as a cloud of quantum possibilities because the chair is not isolated enough for those possibilities to remain delicate and usable. At your scale, the world has already been simplified. It has been filtered into stable shapes, durable records, and practical facts. This is why the present feels so clean. Not because the universe is necessarily built from a single universal now, but because your level of reality has been compressed into one, and relativity adds another quiet crack to the old picture. According to Einstein's theory, there is no single universal present shared by the entire cosmos. Two events that seem simultaneous to one observer may not be simultaneous to another observer moving differently. This is not a psychological illusion. It is a measured feature of space-time. The universe does not appear to carry one cosmic clock announcing the same now everywhere. Instead, every observer has their own local ordering of events, depending on motion and position. That means your present is deeply real for you, but it may not be the absolute present of the universe, because physics does not seem to require such a thing. Your now is local, practical, embodied. It belongs to your path through space-time, not to a grand universal spotlight sweeping across all existence. And even inside your own mind, the present is not as instant as it feels. Your brain does not receive the world all at once. Light, sound, touch, balance, memory, and expectation arrive through different pathways at different speeds, and the brain binds them into a single experience. What you call the present is partly constructed from a small window of integration, a brief blending of signals that lets the world feel continuous instead of fragmented. When you hear a voice and see a face move, your brain quietly aligns the signals so they belong to one moment. When you move your hand, your nervous system predicts and corrects, so the action feels immediate. The present you experience is not raw time. It is edited time. It is the brain's best usable summary of what is happening close enough together to matter. This does not make the present fake. A shortcut can still be real and necessary. A map is not the landscape, but without it, you may never find your way. The present may be like that. Not the deepest structure of time, but the form time takes when a living system needs to act, choose, remember, and survive. Without a present, you could not respond to danger, follow a sentence, hold a melody, or feel yourself as one continuous being. Consciousness may need to gather the world into now, because action cannot wait for the full truth of physics. You do not need the complete quantum and relativistic structure of reality to catch a falling glass. You need a simplified moment, a local stage, a practical frame where decision becomes possible. And perhaps that is the beauty of it. The present may not be fundamental, but it is where meaning becomes usable. The universe may not have one single glowing now, yet you do. Your body makes one. Your brain protects one. Your attention lives inside one. So the present moment may be a classical shortcut, yes, but it is also the doorway through which a vast and difficult universe becomes intimate enough to touch. It is reality reduced to something a human life can hold, not the whole truth, perhaps, but the part of truth where you can breathe, notice, choose, and briefly feel the impossible depth of existence arriving as this. Time could emerge from entanglement. What if time is not a river flowing through the universe, but a relationship that appears only when one part of reality becomes linked with another? This is the strange doorway opened by the idea that time could emerge from entanglement, one of the deepest and most beautiful features of quantum physics. Entanglement means that two quantum systems can share a single connected description, even when they are separated, so that what can be said about one is tied to what can be said about the other. It is not ordinary communication, and it is not a hidden wire sending messages faster than light. It is a deeper kind of correlation, a shared physical condition where the parts cannot be fully described as independent things. Usually we think of entanglement as a mystery about distance, as if two particles remain strangely linked across space. But some physicists have explored an even more unsettling possibility. Perhaps entanglement is also connected to the feeling of time itself. In ordinary life, you imagine time as the background against which relationships happen. First there is time, then things meet, separate, influence one another, and change. But quantum theory allows the opposite question. What if some sense of time comes from the relationships? What if before and after are not written into reality from the beginning, but arise when systems become correlated, when one physical thing can function as a reference for another, when the universe starts to contain internal patterns that can be read like a clock? To understand this without drowning in mathematical language, imagine two dancers in a dark room. If you see only one dancer frozen in a single pose, there is no dance for you to follow. But if you can compare one dancer's movement with the other, rhythm appears, sequence appears. One turn makes sense relative to another. The dance is not located in either dancer alone. It lives in the relationship between them. Some ideas in quantum foundations treat time in a similar spirit. A system may not need an outside ticking background to have meaningful change if it is entangled with something that can serve as a clock. The clock is not necessarily a metal object on a wall. It can be any physical system whose changing state can be compared with another system. When one part of a larger quantum whole is used as a reference, the other part can appear to evolve relative to it. From the viewpoint of the full combined system, the description may be more static or timeless. But from inside the relationship between the parts, a flow-like experience can emerge. This is not a proven final answer to the mystery of time, and honest science must say that clearly. It is a serious theoretical idea, not a settled fact. But it is powerful because it offers a way to think about time without pretending there is always a perfect cosmic clock outside everything. In a universe that contains all things, any clock must also be part of the universe. So time may not be something imposed from beyond reality. It may be something reconstructed from within reality, from correlations among its parts. Entanglement becomes important here because it is the strongest kind of quantum relationship we know. It can make the state of one system meaningful only together with another. If a clock system and another system are entangled, then the condition of the clock can be tied to the condition of what it measures. You do not simply ask, what is the system doing at this absolute time? Instead, you ask, when the clock part has this state, what is the other part like? That small shift changes the entire emotional shape of the question. Time becomes less like an invisible ruler laid across the universe and more like a pattern of mutual reference. It is not that nothing changes. It is that change may be defined through comparison. This also connects to a broader and still developing idea in modern physics. Maybe the fabric of reality is not built primarily from isolated objects, but from information and relationships. Entanglement already plays a major role in quantum information, quantum computing, and some approaches to understanding space-time itself. In certain areas of theoretical physics, researchers have found deep links between patterns of entanglement and the shape or connectivity of space. Time is more difficult and more subtle, but the same lesson keeps returning in different forms. Reality may not begin with separate things placed inside a finished stage. The stage-like features may grow out of how the parts are connected. If space can be tied to patterns of entanglement, then perhaps time too is not merely a container, but a phenomenon that appears when relations become organized enough to support order, memory, and comparison. This is where the idea becomes quietly mind-changing. You have always felt time as something that carries relationships away. People meet, drift apart, remember, forget. Stars form, burn and fade. Cells divide, bodies age, voices change. But this view suggests that relationship may come first. The links between things may be what allows sequence to mean anything at all. Without correlation, there is no useful clock. Without one system changing relative to another, there is no measurable duration. Without records connecting one state to another, there is no experience passage. Time, then, may be less like a road under your feet, and more like the spacing between footsteps. Less like a container holding events, and more like the order that appears when events become physically connected. And still, we must be careful. Entanglement does not mean consciousness creates time by wishing it into existence. It does not mean human emotions can control clocks. It does not mean all mystical claims about connection are suddenly proven by physics. The real idea is more disciplined and more fascinating. In quantum theory, especially when thinking about the universe as a whole, time might be relational. It might emerge from how physical systems are correlated, rather than existing as an independent flow outside them. This is a scientific possibility explored through careful theory, not an invitation to abandon evidence. And because it is careful, it becomes even more beautiful. It tells you that the world may be stranger without becoming irrational. It suggests that the deepest things may be built not from lonely pieces, but from shared structure. A single note does not make a melody. A single point does not make a distance. A single isolated state may not make time. Time may require relation, comparison, entanglement, a way for one part of reality to say something meaningful about another. And perhaps that is why the idea feels so hauntingly close to human experience. Your own sense of time is also relational. A minute feels long when you are waiting, short when you are absorbed, heavy when you are grieving, light when you are loved. The clock on the wall may count evenly, but lived time is shaped by connection, to your body, to memory, to expectation, to the people and places that give moments weight. Quantum physics does not reduce human feeling to entanglement, and we should not blur those levels too casually. But it does offer a deep echo. Time is never simply numbers. It becomes meaningful through relation. So when you hear that time could emerge from entanglement, imagine the universe not as a machine ticking in emptiness, but as a vast web of physical relationships learning how to order itself from within. Imagine that what you call a moment is not a bead sliding along a string, but a pattern becoming readable because one part of reality is linked to another. And if that is even partly true, then time is not just the thing that separates events. It is the quiet language relationships use to become a world. The Page-Wootters mechanism treats time as relational. Imagine opening a universe-sized book where nothing on the page is moving, yet the moment you choose one sentence as a clock, the rest of the story begins to unfold. This is the strange and elegant idea behind the Page-Wootters mechanism, a proposal in quantum physics that treats time not as a universal stream flowing outside reality, but as something that appears through relationships inside reality itself. In ordinary thinking, you imagine the universe changing because time passes. Time comes first, change follows, and everything from atoms to galaxies is carried along by that invisible current. But Don Page and William Wootters suggested a different way to look at the problem. Perhaps the universe as a whole can be described in a timeless way, while parts of the universe still experience change relative to other parts. That sounds contradictory at first, almost like saying a movie can be still and moving at once. But think of the difference between holding an entire film reel in your hands and watching it frame by frame through a projector. The reel, as a whole, contains every frame together. Nothing needs to flow inside your hand, yet when one frame is compared with the next, motion appears. The Page-Wootters idea works with a similar kind of shift. It asks us to stop demanding an outside clock for the entire universe, because if the universe includes everything, there is no outside place where such a clock could sit. Instead, one part of the universe can be used as a clock, and another part can be described according to what that clock part shows. The important word here is relative. A system does not simply evolve against an absolute time floating beyond all things. It evolves relative to another physical system that plays the role of a clock. If the clock reads one condition, the rest of the system appears one way. If the clock reads another condition, the rest appears another way. From inside that relationship, change becomes meaningful. From the view of the total combined quantum state, the whole thing may look frozen, balanced or stationary, not because nothing exists, but because all the correlations are held together in one complete structure. The flow appears when you ask a conditional question. When the clock is like this, what is the world like? This is a very different picture from the one your senses give you. You are used to clocks measuring time as if time already exists independently. A clock on a wall seems to reveal an external fact, the way a signpost reveals a road. But in the Page-Wootters view, the clock is not standing outside the universe pointing at time. It is inside the universe, physically connected through quantum correlations with what it helps describe. Time becomes less like a road and more like a comparison. It is not the clock alone. It is not the system alone. It is the pattern between them. This is why the mechanism is often described as relational time. The universe does not need to be pushed forward by a hidden master clock if its internal parts can serve as references for one another. And this matters deeply for quantum gravity, because theories that try to describe the whole universe can run into the problem that time seems to disappear from the deepest equation. The Page-Wootters mechanism offers one possible way to understand how ordinary time could still appear for observers inside such a universe. It says, in effect, that even if the whole quantum universe does not evolve with respect to an outside time, subsystems inside it can still show evolution with respect to each other. A clock part and a world part can be entangled in such a way that the world appears to change when read relative to the clock. This is not the same as saying time is an illusion in a careless sense. The change is real for internal observers. The correlations are real. The clock readings are physical. What changes is the explanation of where time comes from. Time is not assumed at the foundation. It is reconstructed from within. To make this more tangible, imagine you are trapped inside a perfectly sealed room with no windows and no connection to anything outside. If you want to measure change, you cannot appeal to an external sunrise or a cosmic clock beyond the walls. You must use something inside the room, a dripping tap, a swinging pendulum, a burning candle, your heartbeat. The room's events become ordered by comparing them to one internal process. Now stretch that idea to the entire universe. There is no outside sunrise beyond all existence. There is no before the universe clock ticking in another room. So if time exists for us, perhaps it must be built from internal comparisons, from one part of reality acting as a reference for another. The Page-Wootters mechanism turns that simple intuition into a quantum idea. It suggests that the feeling of evolution can arise from correlations within a larger state that, taken as a whole, does not need to evolve in the usual way. The beauty of this idea is also its difficulty. It does not hand us a finished theory of everything. It does not solve every problem about time. Physicists still debate how far the mechanism can go, what kind of clocks are needed, how realistic those clocks can be, and how this connects to gravity, measurement, and the universe we actually observe. But it gives us a serious, disciplined way to imagine time without placing it outside the universe like a supernatural metronome. It keeps the science grounded while allowing the mystery to breathe. And perhaps the most mind-opening part is that it changes what a clock means. A clock is not merely an object that counts. A clock is a physical system that lets other systems be ordered. Its power comes from relationship. If nothing were compared with it, its ticking would have no meaning. If there were no changing world around it, a clock would be a rhythm with no listener, a ruler with nothing to measure. In the Page-Wootters picture, time is born not from ticking alone, but from the way ticking becomes correlated with the rest of reality. This has a quiet emotional echo, even though the physics itself remains precise. Your life also feels continuous because parts of you serve as clocks for other parts. Breath against thought, heartbeat against fear, memory against change, aging against desire. You do not experience time as an abstract dimension. You experience it as relation. Waiting feels long because your expectation becomes a clock. Grief feels slow because the mind keeps comparing the present to a world that used to exist. Joy feels brief because attention stops counting for a while. Human experience is not quantum theory, and we should not confuse the two, but there is a shared lesson in the language of relation. Time is meaningful only when something is compared with something else. The Page-Wootters mechanism asks you to imagine the entire universe this way, not as a machine moving through an external flow, but as a complete quantum structure whose internal relationships allow beings like us to feel sequence, duration, and change. So when you hear that this mechanism treats time as relational, do not picture a universe where nothing happens. Picture a universe where happening is not imposed from outside, but read from within, where one part of reality becomes the clock by which another part becomes a story, where the whole may be still in a deep mathematical sense, yet alive with internal perspectives. And maybe that is the softest shock of all. Time may not be the thing that makes relationships possible. Relationships may be the thing that makes time possible. Quantum clocks are limited by uncertainty. The more perfectly you try to make a clock, the more quantum physics reminds you that precision has a price. At first, a clock seems like the simplest promise in the world. It marks one moment after another, dividing the invisible flow of change into numbers you can trust. A clock on the wall may be imperfect, a phone clock may drift without correction, and even a mechanical watch slowly loses its rhythm. But you might imagine that if technology became advanced enough, if the parts were small enough, cold enough, isolated enough, then a clock could become almost godlike in its accuracy. Modern atomic clocks already come astonishingly close. They do not rely on swinging metal hands or turning gears, but on the steady transitions of atoms, especially the way electrons in certain atoms shift between energy levels with frequencies so regular that they can define the second itself. These clocks are among the most precise instruments humans have ever built. They can measure tiny differences in time caused by height, gravity, motion, and even the slow lifting of one clock just a little above another. Yet when you follow precision all the way down into the quantum world, you do not find unlimited certainty waiting at the bottom. You find a boundary. Not a boundary caused by sloppy engineering, weak materials, or human clumsiness, but a boundary woven into the structure of measurement itself. A quantum clock is limited by uncertainty because the very systems that make it tick are quantum systems, and quantum systems cannot reveal all their properties with infinite sharpness at the same time. This is not a vague philosophical statement. It is part of how nature behaves. To build a clock, you need something that changes regularly, something that can act like a rhythm. In atomic clocks, that rhythm comes from the frequency associated with a transition between two quantum energy states. But to measure that frequency with extreme accuracy, you need time. The longer you observe a stable rhythm, the better you can estimate it. If you listen to only a fraction of a musical note, it is harder to know its exact pitch. If you listen longer, the pitch becomes clearer. Quantum clocks work with a similar trade-off. A very short measurement can tell you when something happened with good timing, but it may leave more uncertainty in the energy or frequency involved. A longer measurement can sharpen the frequency, but it spreads out the timing. Nature resists giving you perfect sharpness in both. This is often connected to time-energy uncertainty, though it is important to say carefully that time in quantum physics is not exactly like position, and energy is not exactly paired with time in the same simple way that position and momentum are paired. Still, the practical message is real. There are limits to how sharply a quantum system can define timing and energy-related change together. The clock must use physical resources, and those resources come with quantum noise. Even if you cool atoms to extreme temperatures, isolate them from vibrations, shield them from stray fields, and use lasers of breathtaking stability, you still face the fact that each measurement has statistical uncertainty. A single atom cannot give you a perfectly smooth tick forever. It behaves according to quantum probabilities. That is why the best atomic clocks often use many atoms. By averaging over large numbers of quantum systems, scientists can reduce uncertainty, the way many quiet voices can reveal a clearer pattern than one uncertain whisper. But even then, there are limits. The atoms can interact with one another. The measuring light can disturb them, and quantum projection noise can appear when the act of reading the atoms forces their uncertain states into definite outcomes. The clock becomes more precise, but never escapes being physical. It is not a pure idea counting from outside the universe. It is matter trying to measure change while obeying the same rules as everything else. Some researchers use entangled atoms or squeezed quantum states to push beyond ordinary measurement limits, redistributing uncertainty so that the clock becomes more sensitive in the variable that matters most. This is real and powerful, and it shows that quantum uncertainty is not only an obstacle, it can also become a tool when handled carefully. But even these methods do not erase uncertainty from existence. They rearrange it, they manage it, they make a bargain with it. The deeper you go, the more timekeeping becomes an art of negotiating with nature's limits. And there is another layer. A clock must have energy to tick and must be distinguishable from one moment to the next. If its states are too similar, it cannot tell time well. If you want sharper timing, you often need more energy, more particles, more coherence, or a longer observation. Precision is never free. It must be paid for in stability, isolation, information, and physical resources. This gives quantum clocks a strange dignity. They are not just machines. They are careful agreements between uncertainty and order. They show that time, as measured by physics, is not handed to us with infinite resolution. It is extracted from the world through delicate comparison. Each tick is not a perfect cut in reality, but a refined estimate made by atoms, fields, light, and probability working together. And perhaps that is why this topic feels quietly humbling. You live as if moments have sharp edges. You say now, then, soon, too late, not yet, as if life were divided into clean pieces. But the most precise clocks ever built suggest that even the act of dividing time has a softness at its foundation. Not softness in the sense of weakness, but softness in the sense of depth. A limit where certainty becomes statistical, where rhythm becomes quantum, where the clean tick of a clock is supported by countless uncertain events carefully arranged into trust. So when you imagine a quantum clock, do not picture an instrument failing to reach perfection. Picture one of humanity's most beautiful attempts to listen to nature's rhythm as closely as possible, and to discover that the rhythm is real, but never infinitely sharp. Every clock is a question asked of the universe. How much has changed? And quantum physics answers with astonishing precision, but never with absolute silence behind it. There is always a faint grain, a whisper of uncertainty, reminding you that time may be measured more and more beautifully, but never owned completely. Time-energy relations are not like position-momentum. Time and energy seem like they should form a perfect pair, like position and momentum, but quantum physics hides a subtle trap here. The resemblance is real enough to be useful, and different enough to mislead you if you treat it too simply. You may have heard that quantum uncertainty means you cannot know certain pairs of things with perfect precision at the same time. The most famous pair is position and momentum. If you try to define exactly where a particle is, you lose sharpness in how its motion is described. If you define its motion very sharply, its location becomes spread out. This is not because your instruments are bad, and it is not because the particle is hiding a secret answer from you. It comes from the wave-like structure of quantum states. A sharply localized wave must be built from many different wavelengths, and many wavelengths mean a spread in momentum. A very clean single wavelength gives a sharp momentum, but it stretches out through space. So position and momentum uncertainty has a deep mathematical symmetry. Both are physical properties of the system. Both can be represented as observables in quantum theory. Both belong to the particle's description in a direct way. But time and energy are not usually like that. This is where the story becomes more delicate. Energy is a property a quantum system can have. It can be measured, arranged into levels, exchanged, conserved, and used to describe how a system behaves. Time, however, is usually not treated as a property of the system in the same way. In standard quantum mechanics, time is more like the parameter used to track change, the background label that says how the quantum state evolves. You do not usually measure the time of a particle the way you measure its position. You measure an event, a duration, a decay, a transition, a clock reading, or a correlation between one process and another. This means the famous time-energy uncertainty relation is not simply a copy of the position-momentum one with different names. It has several meanings depending on the situation, and misunderstanding it can lead to some of the most common myths in popular science. For example, people sometimes say that a particle can borrow energy from the universe for a short time, as long as it gives it back quickly. That phrase may sound exciting, but taken literally, it is misleading. Quantum physics does not allow nature to casually break energy conservation like someone taking a loan from a cosmic bank. In many contexts, energy is conserved very strictly. What the time-energy relation often tells you instead is about the limits of defining energy sharply when a state exists only for a limited time, or about how quickly a quantum system can change if its energy spread is limited. If an unstable particle decays very quickly, its energy cannot be perfectly sharp. There is a natural width to the energy associated with that short lifetime. This is not cheating the rules, it is a wave-like fact. A brief signal cannot have one perfectly exact frequency. A note played for only an instant has a blur of pitch. A long, steady tone can have a much sharper pitch. In quantum physics, energy and frequency are closely connected, so a short-lived quantum state carries an energy width. The less time it exists as a recognizable state, the less sharply its energy can be defined. That is one honest meaning of time-energy uncertainty. Another meaning appears when you ask how fast a quantum system can evolve from one state into a noticeably different one. A system with very little energy spread cannot change arbitrarily fast. There are quantum speed limits, not like a speed limit sign on a road, but like a structural limit on how quickly distinguishable change can happen. Energy is not just fuel in this picture. It is connected to the pace at which quantum states can become different. But again, time here is not an object being measured like position. It is a duration, a measure of change, a question about how long a process takes or how sharply an event can be localized. This is why physicists speak carefully about time-energy relations. They are powerful, real, and experimentally meaningful, but they do not have one single simple form that works exactly like position and momentum in every context. The difference matters because it teaches you something deeper about time itself. Position belongs to a particle's possible location in space. Momentum belongs to how its wave is structured across space. But time sits uneasily in quantum mechanics. It is needed to describe evolution, yet it is not normally placed inside the theory as just another measurable property. You can build clocks out of quantum systems. You can compare processes. You can measure lifetimes with extreme precision. But the role of time remains different from the role of ordinary observables. And at the frontier, where quantum theory meets gravity, this difference becomes even more mysterious. Because relativity tells us time is part of space-time and can be affected by motion and gravity, while quantum theory often treats time as an external label. The result is not a contradiction in everyday experiments, because the framework works beautifully in its proper domain. But it is a clue that our understanding is incomplete. Time does not fit into quantum physics as comfortably as space does. It enters through change, duration, clocks, and correlations, rather than as a simple, measurable thing sitting beside energy like a twin. And perhaps that is why the time-energy relation feels so strange when you slow down and really look at it. It is not just a technical footnote. It is a reminder that not every deep pair in physics is symmetrical in the way human language makes it sound. Words can make time and energy seem like two equal partners holding opposite ends of a rope. The actual theory is more subtle. Energy belongs to the state, while time often describes the unfolding, the interval, the condition under which the state is examined. One is more like a feature of the music. The other is more like the listening through which the music changes. This does not make time less important. It makes it harder to place. In your own life, you feel energy and time as intimately linked. When you are exhausted, hours feel heavy. When you are excited, hours vanish. When something ends too quickly, you sense that its meaning did not have enough time to become clear. Quantum physics is not explaining those feelings directly, but it offers a quiet echo. Duration affects definition. Some things cannot be sharply known if they do not last long enough. A fleeting state carries blur. A brief event resists perfect description. The universe seems to say that precision needs patience, that to know a frequency clearly, you must let the note ring, that even in the smallest physical systems, what something is and how long it can be recognized are deeply connected. So the next time you hear that time and energy are uncertain, do not imagine reality breaking its own rules for a moment and then repairing itself before anyone notices. Imagine something more careful and more beautiful. A world where short-lived states have natural breadth, where change has speed limits, where clocks are physical, where energy remains lawful, and where time refuses to be reduced to just another property on a list. Position and momentum reveal the wave-like spread of things in space. Time and energy reveal something more elusive, that the act of lasting, changing, and being sharply defined are bound together in ways that still point toward one of the deepest unfinished questions in physics. Not simply what moves through time, but what time is allowed to be. Quantum speed limits control how fast change happens. There may be a deepest speed limit in nature that does not tell objects how fast they can travel, but tells reality how fast it is allowed to become different from itself. You already know one famous cosmic limit. Nothing carrying information can move through space faster than light. That limit protects cause and effect across the universe. It keeps a signal from outrunning the structure of space-time. But quantum physics reveals another kind of limit, quieter and less familiar. Not about crossing distance, but about changing state. A quantum system cannot always transform from one condition into a clearly different condition as quickly as you might imagine. Even if you do not ask it to move across a room, even if it sits in one place, even if the change is internal, there are rules governing how rapidly it can become distinguishably new. These are called quantum speed limits, and they are not engineering limits like a weak motor, a slow computer, or a dull measuring device. They come from the structure of quantum evolution itself. At the smallest level, change is not just a thing that happens whenever nature feels like it. Change has a pace, and that pace depends on physical resources such as energy, uncertainty, and how far the system must travel through its own landscape of possible states. Imagine turning a face slowly toward the light. At first, the difference is subtle. A tiny shift does not make it a new face, but turn far enough, and the expression becomes unmistakably different. Quantum systems have a version of this. Two states can be very similar, almost overlapping in what they might produce if measured, or they can be clearly distinct, like two notes far enough apart that your ear no longer confuses them. A quantum speed limit tells us the minimum time required for a system to move from one state to another state that can truly be told apart. This matters because quantum change is not the same as a simple object sliding along a path. A quantum state contains information about what outcomes are possible, how likely they are, and how they relate to one another. To change that state into a very different one, the system needs a kind of physical rotation through possibility space. If the system has more available energy or a wider spread of energy, it may change more quickly. If its energy structure is too narrow or too limited, it cannot instantly become something fully distinct. Nature will not let it jump from one sharply different condition to another in zero time. This is one reason quantum speed limits are so important for quantum computing. A quantum computer works by guiding quantum bits through carefully controlled transformations. If you try to perform operations too slowly, noise from the environment may destroy the delicate quantum information before the calculation finishes. But if you imagine doing every operation infinitely fast, physics refuses. There is a fastest meaningful pace for reliable transformation. An understanding that boundary helps scientists design better gates, better algorithms, and better control methods. In this sense, quantum speed limits are like the hidden tempo of quantum technology. They do not just ask, can this calculation be done? They ask, how quickly can nature allow this calculation to become real? The same idea appears in chemistry and biology at microscopic scales. Chemical reactions depend on quantum transitions, electron rearrangements, tunneling effects, and energy landscapes. A molecule does not change shape or react simply because a human equation says the final state is allowed. It must pass through physically possible transformations, and the speed of those transformations is bounded by the quantum structure of the system. In advanced physics, these limits also help researchers think about black holes, thermodynamics, information scrambling, and how fast a complex quantum system can spread information through its internal parts. Some systems are incredibly efficient at mixing information, almost like a drop of dye spreading through water with impossible speed. Yet even they are believed to face deep bounds. This gives quantum speed limits a strange philosophical weight. They suggest that change itself is not infinitely elastic. The universe may allow vast possibility, but it does not allow every possibility to become distinct instantly. There is a cost to becoming different. There is a minimum duration required for transformation to gain physical meaning. And this is where the idea becomes more than a technical detail. In everyday life, you often imagine change as a matter of will. You want healing now, understanding now, progress now, a new self now. But even at the quantum level, transformation is not simply commanded into existence. It has a rhythm determined by what the system is, what energy it has, how strongly it is driven, and how different the final state must be from the beginning. Of course, human growth is not a quantum transition in a direct scientific sense, and we should not pretend that personal change follows the same equations as an atom or a quantum bit, but the lesson still echoes with surprising clarity. Becoming truly different is not the same as making a surface movement. A tiny shift can happen quickly. A deep transformation requires the system to travel far enough from what it was that the difference becomes real. Quantum speed limits give physics a way to measure that depth. They say that change has geometry, that difference has distance, and that time is not just a passive background, but part of the price paid for transformation. The most beautiful part is that these limits do not make the universe feel smaller. They make it feel more lawful, more textured, more honest. A world without limits would be a world without structure. Anything could become anything instantly, and change would lose meaning because there would be no resistance, no duration, no unfolding. Quantum speed limits preserve the dignity of process. They tell us that even the smallest systems must pass through allowed stages of becoming, not always as a visible storyline, but as a real physical evolution from one distinguishable condition to another. So when you hear that quantum speed limits control how fast change happens, do not picture a particle stopped by a wall or a clock shouting, "too fast." Picture a deeper rule in the architecture of reality, a quiet boundary that says every transformation must take enough time to become physically distinct. Even in the invisible world of atoms, light, and quantum information, change is not free from rhythm. The universe may be strange, uncertain, and full of possibilities, but it still has tempo. And perhaps every moment of transformation, from the flicker of an atom to the unfolding of a thought, carries that same hidden truth. To become something else, reality must spend time becoming. Decoherence helps create a direction of time. A quantum object can begin like a quiet choir of possibilities, but the moment the surrounding world starts listening, the choir loses its harmony and time begins to look one way. This is the heart of decoherence, one of the most important ideas for understanding why the strange quantum world does not usually appear in your kitchen, your hands, or the chair beneath you. At the smallest scales, a system can hold together several possible states in a delicate relationship called coherence. Coherence is what allows quantum possibilities to interfere with one another, not like ordinary alternatives sitting separately in a box, but like waves whose peaks and valleys can strengthen or cancel each other. This is why a particle can produce interference in carefully controlled experiments, why quantum computers need fragile superpositions, and why isolation matters so much in quantum laboratories. But the universe is not a silent room. It is full of light, heat, air molecules, vibrations, radiation, surfaces, and countless tiny interactions. A quantum system almost never stays completely alone. The moment it interacts with its environment, information about its possible states begins to leak outward. A molecule bumps into it, a photon scatters from it, a surrounding field responds to it, and with every tiny contact, the delicate relationships between the possible states become harder and harder to observe. The system may still be quantum in the deepest technical sense, but for any local observer, the interference has effectively vanished. The possibilities stop behaving like one connected choir and start behaving like separate classical alternatives. This is decoherence, not magic, not consciousness forcing reality to choose, not a dramatic collapse caused by human attention, but the physical spreading of quantum relationships into the environment until the original system can no longer show its full quantum pattern by itself. And this helps create a direction of time, because decoherence is overwhelmingly easier in one direction than the other. A clean quantum superposition can quickly become entangled with the environment, scattering its coherence across countless degrees of freedom. But gathering all those environmental traces back together, perfectly reversing every interaction, and restoring the original delicate interference would require almost impossible control. You would have to reverse the motion of every scattered photon, every disturbed molecule, every tiny vibration that carried away a fragment of the system's phase relationship. In principle, under the most ideal laws, some microscopic processes may be reversible. But in practice, once the environment has become involved, the quantum information is distributed so widely that the system looks irreversibly classical. This is where the arrow of time begins to take on a sharper quantum shape. The future is the direction in which coherence tends to spread into the surroundings. The past is the direction in which coherence was more concentrated, more recoverable, less entangled with everything else. Imagine drawing a perfect pattern in fine sand, then letting the wind touch it grain by grain. Nothing supernatural destroys the pattern. The grains still exist, the air still carries motion, but the original shape becomes swallowed by countless tiny changes, each one too small to track, together making return almost impossible. Decoherence does something like this to quantum possibilities. It does not necessarily erase all information from the universe, but it removes the visible interference from the system you were watching. It turns the fragile quantum maybe together into the stable classical this or that you can experience. This is why everyday objects do not appear to be invisible superpositions. A dust grain floating in sunlight is constantly struck by photons and air molecules. A warm object radiates heat. A human body is an enormous storm of interactions. Any delicate quantum coherence between large-scale alternatives would decohere fantastically quickly. The environment is measuring, in a broad physical sense, all the time. Not measuring with intention, not with a mind, not with a scientist writing notes, but measuring by interaction, by becoming correlated with the object's state. That is why the classical world feels firm. It is not because quantum physics stops being true at large scales. It is because large systems are so deeply connected to their environments that their quantum alternatives lose the ability to interfere in any observable way. Decoherence helps explain how the familiar world emerges from the quantum one without pretending there is a simple boundary where nature suddenly changes its rules. The same laws continue, but the appearance changes because the system is no longer isolated enough to preserve coherence. And this is important for time because a world with stable records needs decoherence. A photograph records an event because light interacted with a scene and then with a sensor. Your memory forms because physical changes occur in your brain. A detector click becomes a fact because a tiny quantum event is amplified into a larger chain of environmental records. These records point in one direction. They are created by interactions spreading outward, not by the environment spontaneously arranging itself to erase every trace and return the system to its earlier coherent state. Decoherence, therefore, helps explain why results feel definite, why histories become stable, and why the world seems to move from fragile possibility toward recorded actuality. It does not solve every mystery of measurement on its own, and physicists still debate how to interpret what really happens when one outcome is observed rather than another. But decoherence gives a powerful, evidence-based account of why interference disappears and why the classical world is so persistent. It tells us that the direction of time is not only about broken cups, cooling tea, or disorder in a general sense. It is also about the loss of accessible quantum harmony into the environment. The universe becomes classical looking because it is constantly leaving fingerprints on itself. And once those fingerprints multiply, the world becomes harder to rewind. There is something quietly profound in that. The stable reality you trust may be built from countless vanished coherences, countless delicate quantum relationships dispersed into the surroundings before you ever notice them. The chair beneath you, the room around you, the screen glowing in front of you. All of it appears definite because it is not alone. It is embedded, touched, illuminated, warmed, recorded. The world becomes clear by losing certain kinds of quantum subtlety. Time gains direction because the environment keeps absorbing the hidden relationships that would be needed to make the alternatives sing together again. So when you think of decoherence, do not imagine a simple switch from unreal to real. Imagine a whisper spreading into a crowd until it can no longer be heard as one voice. Imagine possibility becoming history because the universe cannot stop interacting with itself. And perhaps that is the softest way to understand why time feels like it moves forward. Not because every deep law shouts forward, but because the fragile harmonies of the quantum world are always spilling outward, becoming records, becoming surroundings, becoming the classical reality you wake into and call now. Entanglement growth can make time feel irreversible. A universe can obey reversible quantum rules at its deepest level and still feel impossible to rewind because its parts keep becoming more and more entangled with one another. This is one of the quiet ways time gains weight in quantum physics. Not because the whole universe necessarily loses information in a simple way, but because information becomes shared across so many connections that no small part can recover its original innocence. Imagine a few musicians playing separate notes in an empty room. At first you can hear each instrument clearly. The violin here, the piano there, the soft drum beat underneath. But as the music grows more complex, the sounds blend into one another. Harmonics overlap, echoes bounce from the walls, The room itself becomes part of the sound. Nothing has vanished exactly, but the clean separateness you began with is gone. Entanglement growth works with a similar kind of deep blending, though in a far more precise quantum sense. When quantum systems interact, their states can become linked so that one part can no longer be fully described without referring to the rest. At the beginning, two particles or two regions of a system might be nearly independent. You can speak about one without knowing much about the other. But as interactions continue, correlations spread. A particle becomes linked with its neighbor, that neighbor with another, then another, until information about any one part is no longer stored locally. It is distributed across the whole. From the viewpoint of the complete system, the underlying quantum evolution may still be orderly and, in principle, reversible. But from the viewpoint of a small observer looking at only one part, the situation begins to look irreversible. The local piece seems to lose its purity. Its behavior starts to resemble randomness, warmth, or equilibrium. Not because the laws have become careless, but because the information needed to describe it completely has escaped into its relationships with everything around it. This is why entanglement growth is so important for understanding how isolated quantum systems can appear to thermalize. Thermalization means that a system settles into behavior that looks like it has a temperature, where small parts look ordinary, mixed, and predictable in a broad statistical way, even if the whole system is still evolving according to quantum rules. For a long time, thermalization was often associated with contact with an outside environment, like a hot object cooling in a room. But quantum many-body physics asks a subtler question. Can a completely isolated quantum system become locally thermal just because its internal parts become entangled with one another? The answer in many cases appears to be yes. If you look only at a small region, that region can behave as if it has forgotten its starting condition, because the details of that starting condition are now encoded in complicated correlations spread across the rest of the system. The information is not necessarily destroyed, it is scrambled. And scrambling is what makes the past so hard to reconstruct. Picture dropping a tiny amount of ink into a glass of water, but instead of focusing on ordinary mixing, imagine the quantum version. The identity of the original state becoming woven into relationships among countless microscopic parts. If you had godlike access to every part of the glass and infinite control over every interaction, perhaps you could reverse the evolution and bring the state back. But any realistic observer has access to only a small slice. To that observer, the information is gone. The arrow of time appears as a limit of access, a widening gap between what exists in the full quantum pattern and what can be recovered from any local piece. This is why entanglement growth feels like a bridge between quantum law and lived irreversibility. The deep equations may not shout, forward only, but the spread of entanglement makes backward motion practically unreachable. Every interaction creates a wider web. Every correlation ties the present more tightly to a history that cannot be locally unknotted. In advanced physics, this connects to ideas like entanglement entropy, which roughly measures how strongly a part of a system is entangled with the rest. When that entanglement increases, the part looks more mixed when viewed alone. It is as if the local system has lost its private identity and become meaningful only as part of a larger whole. That does not mean it becomes vague in a mystical way. It means its full description now lives in shared information, not in isolated properties. This helps explain why the future often feels different from the past. The past, in a low entanglement beginning, can be simpler to summarize. The future, after many interactions, contains more distributed correlation. The world becomes harder to compress into a neat local story. And perhaps this is one of the most profound things quantum physics teaches. Irreversibility may not require the universe to break its own rules. It may arise because the rules allow connection to grow so richly that no small part can return by itself. There are even special systems where entanglement does not grow normally, or where parts of a system can avoid thermalizing for surprisingly long times. These exceptions are fascinating because they show that irreversibility is not a cheap assumption. It depends on the structure of interactions, the spread of correlations, and the way information moves through the system. Some systems scramble quickly, others preserve memory. Some behave like smooth roads toward equilibrium. Others hold hidden pockets of order. This means the direction of time is not just a philosophical feeling. It is tied to detailed physical mechanisms, to how nature stores and shares information. And when you step back, the emotional shape of the idea becomes quietly powerful. You often think of time as what takes things away, but entanglement growth suggests another view. Time is also what binds things together so deeply that their earlier separateness cannot be restored. A moment passes, and the world does not merely move on. It becomes more internally related. A sound enters a room and becomes part of the air, the walls, the ears that heard it. A choice enters a life and becomes part of memory, habit, consequence, and response. Human life is not literally a controlled quantum many-body experiment, and we should not force the metaphor too far. But the scientific lesson still resonates. Once information is widely shared, return becomes difficult. Not because reality forgets, but because it remembers too broadly. So when you hear that entanglement growth can make time feel irreversible, imagine the universe not as a machine losing pieces, but as a vast tapestry gaining threads. The more the threads cross, the harder it becomes to pull one strand back to where it began without moving the entire cloth. The past is not simply destroyed, it is woven into the whole. And maybe that is why time feels so one-directional from inside the universe. Not because the deepest laws cannot be reversed in principle, but because every second spreads the story into more connections than any single observer can ever gather back. Loschmidt echoes ask whether time can be reversed. If you could whisper a command to every particle in a room and make each one reverse its motion perfectly, would the room travel backward into its own past? Or would time still find a way to escape? This is the unsettling question behind Loschmidt echoes, a concept that turns the idea of time reversal from a fantasy into a careful physical test. The name reaches back to Joseph Loschmidt, a 19th century physicist who challenged a simple version of the idea that nature must always drift toward disorder. If the microscopic laws of motion can be reversed, he asked, then why could the world not run backward? Why could the scattered molecules of a gas not gather again into one corner? Why could heat not flow back into one object? Why could an apparently irreversible process not undo itself if every tiny motion were reversed with perfect accuracy? This became known as Loschmidt's paradox, and it strikes at the heart of how time's arrow emerges from laws that often look reversible at the smallest scales. A Loschmidt echo is a modern way of asking that question in the laboratory. You take a system, let it evolve forward for a while, then try to reverse the conditions so it evolves backward, and then you ask, how close does it return to where it began? The echo is the returning signal, the trace of the original state coming back after the system has been sent forward and then pushed in reverse. It is like shouting into a canyon and listening not only for whether the sound returns, but whether it returns with the same shape, the same sharpness, the same identity it had when it left your mouth. In ordinary life, reversal looks impossible. You cannot unspill milk by reversing one spoon. You cannot rebuild a shattered plate by wishing every fragment into its old path. But in controlled physical systems, especially in magnetic resonance experiments, echo-like reversals are real. Spin echo experiments, for example, can make a collection of atomic or nuclear spins that have drifted out of sync partially come back into alignment, producing a measurable return of signal. This does not mean time itself has been reversed like a movie. It means scientists can reverse or refocus certain parts of a system's evolution well enough to recover information that seemed to have faded. That distinction is important. Loschmidt echoes are not science fiction time machines. They are precision experiments and theoretical tools that reveal how fragile reversibility really is. In quantum physics, the idea becomes even more delicate. A quantum state can be allowed to evolve under one set of conditions. Then scientists try to apply a reversed version of those conditions and see whether the state returns. If the reversal is perfect and the system is perfectly isolated, quantum theory says the original state could, in principle, be recovered. But the word perfect is doing almost impossible work. Any tiny error in the reversal, any small interaction with the environment, any uncontrolled disturbance, any hidden complexity in the system can weaken the echo. The return becomes incomplete. The original signal fades, and that fading is not just a technical annoyance. It is a window into the stability of reality's memory. Some systems are forgiving. Slight imperfections still allow a strong echo. Other systems are extremely sensitive, especially systems that behave chaotically or contain many interacting parts. In those cases, a tiny mismatch between the forward evolution and the attempted reverse evolution can grow into a large difference, making the system fail to return. This is one reason Loschmidt echoes are used to study quantum chaos, information scrambling, and the boundary between reversible microscopic rules and irreversible macroscopic experience. They let physicists ask how quickly a system forgets its starting point when the reversal is not exact. They also help test how quantum information survives, spreads, and becomes inaccessible. In some experiments, scientists can see echoes weaken in ways that reveal how strongly a system interacts internally, how noisy the environment is, or how sensitive the dynamics are to small perturbations. The beautiful part is that the echo makes the problem of time feel almost audible. You send a system away from itself, then invite it home. If it returns clearly, reversibility has survived. If it returns faintly, something has been dispersed. If it barely returns at all, the system has not necessarily destroyed the past, but it has hidden it inside complexity so deep that practical recovery becomes nearly impossible. This is where Loschmidt echoes teach a lesson different from simple entropy or simple disorder. They show that the arrow of time is not only about things becoming messy, it is also about how hard it is to undo motion when the world contains many parts, many interactions, and many chances for tiny errors to matter. A reversed law is not enough. You need reverse conditions. You need near-perfect control. You need isolation from the rest of the universe. You need every relevant piece to cooperate, and the larger the system becomes, the more unreal that demand feels. A few spins in a laboratory can be refocused. A carefully engineered quantum system can show a partial return, but a warm room, a living body, a broken cup, a day of your life, these are not isolated toys. They are open to air, light, heat, memory, friction, sound, and countless microscopic influences. To reverse them, you would not merely need to run one equation backward. You would need to gather the entire world's scattered involvement and turn it around without a single mistake. That is why the past feels unreachable. Not because nature always forbids reversal in principle, but because reversal requires a precision so extreme that the universe becomes its own obstacle. And this makes Loschmidt echoes strangely moving. They do not simply ask whether time can be reversed. They ask what kind of world would be required for reversal to mean anything. They show that the past is not just gone in a poetic sense. It is often encoded in such a vast and fragile pattern of details that no local hand can restore it. Yet the existence of echoes also means the past is not always erased as completely as it feels. Under the right conditions, traces can return, order can reappear, a signal can revive after seeming lost, the universe for a moment can answer backward. So when you hear the phrase Loschmidt echo, imagine not a clock spinning in reverse, but a question sent into the deepest structure of change. If we undo the rules, will reality come back to itself? Sometimes it does, softly, partially, beautifully. Sometimes it does not, and in that difference, you glimpse why time has the emotional shape it has for beings like us. The future opens because the world can still spread into new complexity. The past closes because returning would require the impossible recovery of every whisper the moment left behind. A Loschmidt echo is the sound of physics testing that closure, listening carefully to see whether time's locked door is truly locked, or whether, under rare and delicate conditions, it can still tremble with the memory of opening. Recurrence theorems suggest systems can nearly return. A universe that seems to spend every moment moving away from what it was may, under the right conditions, carry a hidden promise that it can almost come back. This is the strange message of recurrence theorems. Ideas in physics and mathematics suggesting that certain systems, if they are finite, isolated, and allowed to evolve long enough, can return arbitrarily close to a previous state, not perfectly in the everyday sense, not like a film rewinding with clean dramatic certainty, but close enough that the old arrangement becomes almost recognizable again. At first, this feels impossible. You watch cream spread through coffee, dust drift through sunlight, weather change, bodies age, memories soften, and galaxies move across cosmic time, and everything seems to insist that return is not the natural direction of things. The world looks like a one-way dispersal machine, but recurrence theorems ask you to imagine a different kind of situation. A system with limited possible states, no outside disturbance, no energy leaking away, no fresh randomness being poured in from the environment. In such a closed and bounded system, the motion may wander through an enormous landscape of possible arrangements. But if the landscape is not infinite in the relevant way, then the system cannot keep visiting entirely new places forever. Eventually, after a time so long it can make ordinary cosmic ages feel like a blink, it must come back near somewhere it has been before. This is often associated with the Poincaré recurrence theorem in classical mechanics. The idea is not that a broken cup on your floor will reassemble tomorrow, or that your life will repeat next Tuesday, or that the universe behaves like a neat loop with a scheduled restart. The real lesson is more precise and more unsettling. Irreversibility can be practical, overwhelming, and emotionally absolute from inside life, while still not being the same as mathematical impossibility in idealized systems. A gas in a perfectly sealed box, if described by reversible microscopic laws and given enough time, may pass extremely close to a previous arrangement. A quantum system with certain bounded energy conditions can also show recurrences, where its state returns close to its starting form after long intervals. These are not everyday events, because the required times are usually absurdly enormous. For any system with many particles, the recurrence time can grow beyond imagination, far longer than the current age of the universe, longer than any scale that feels physically useful for human life. That is why recurrence does not rescue you from ordinary time's arrow. It does not make spilled ink gather back on the page while you wait. It does not make aging reversible in the real world. It reveals something subtler. The laws may allow near return in principle under ideal conditions, while the world you inhabit is so open, complex, and constantly interacting that such return becomes practically unreachable. The distinction matters. Physics often lives in the tension between what is possible in principle and what is possible in the universe as it actually touches you. A recurrence theorem assumes a kind of isolation that real macroscopic objects almost never enjoy. Your room is not sealed away from light, gravity, heat, air, radiation, and the rest of the cosmos. Your body is not a closed mechanical toy. Even a laboratory system must fight noise, measurement, and environmental interaction. So the recurrence theorem is not a promise of personal repetition. It is a window into the deep structure of reversible dynamics. It says that if a system is trapped inside a finite range of possibilities and evolves without losing itself to the outside, then wandering long enough can bring it home, or almost home. But almost is important. In complex systems, returning close to a previous state does not necessarily mean every meaningful detail returns. A tiny difference can matter enormously. A world almost like yesterday is not yesterday if the one detail you care about is missing. A face almost remembered is still not the person standing there. And in quantum physics, returning close can mean the mathematical state overlaps strongly with an earlier one. Not that a familiar scene reappears in human terms. This is where recurrence becomes both scientific and haunting. It suggests that the universe may contain deep loops of possibility, but not necessarily loops of meaning. Nature may nearly repeat arrangements without repeating the story your mind attaches to them. The same mathematics that allows return also shows how rare and fragile that return can be. If you wait long enough in an ideal system, the pattern may revisit itself, but the waiting time can be so vast that the word eventually loses its comfort. Eventually can mean beyond stars, beyond planets, beyond memory, beyond any observer able to care. This is why recurrence sits so strangely beside entropy. Entropy tells you that systems overwhelmingly move toward more probable arrangements, toward states with many microscopic ways of looking the same from the outside. Recurrence says that in an ideal finite system, even extremely unlikely near returns are not forbidden forever. The arrow of time is therefore not a simple wall. It is more like an almost endless slope, one that can contain rare mathematical echoes, but still governs every practical step you take. And perhaps this is what makes the idea so quietly powerful. It does not erase the passage of time. It makes the passage of time feel deeper. It shows that what you call never may sometimes mean so unlikely, so delayed, so condition-dependent, that no life could ever wait for it. It teaches humility about the difference between law and experience. The universe may allow structures that your heart can never use. It may permit near return without granting restoration. It may carry the possibility of echoes without offering reunion. So when you hear that recurrence theorem suggests systems can nearly return, do not imagine a comforting loop where everything lost is handed back. Imagine instead a vast sealed music box, playing through an almost endless number of hidden configurations, and somewhere beyond all ordinary patience, a few notes nearly align with the song it once played. The melody is not truly repeated, but it is close enough to make you wonder whether time is less like a straight road and more like an immense wandering through possibility. And maybe that is the final lesson. The past may be practically unreachable, but physics does not always describe it as absolutely erased. In rare, ideal, almost unimaginable circumstances, the shape of what was can come near again. Not as memory, not as destiny, but as a mathematical echo drifting through the deep patience of nature. Thermal time, links, temperature and flow. Heat may be more than a sign that particles are restless. In one of the strangest ideas at the edge of quantum gravity, heat may help tell the universe which way time flows. You normally think of temperature as something secondary, almost ordinary. The warmth of a cup in your hands, the coldness of night air, the fever of a body, the glow of a star. Temperature seems like a measurement inside time, not a source of time. First, you imagine time passing. Then, within that passage, hot things cool, cold things warm, and energy spreads. But the thermal time idea reverses the intuition in a careful and radical way. It asks whether the flow we call time might be extracted from the thermal state of a system itself, rather than assumed from the outside. This idea is known as the thermal time hypothesis, developed by Alain Connes and Carlo Rovelli, and its central claim is not that heat magically creates clocks, but that in a generally covariant quantum theory, where no single external time is given in advance, the physical flow of time may be determined by the thermodynamic state of the system. That phrase can sound difficult, so let it slow down. A system has things that can be observed: energies, fields, positions, correlations, changes in measurable quantities. Physicists can describe the structure of these observables. But if there is no outside cosmic clock, how do you decide what counts as the natural flow from one condition to another? The thermal time hypothesis says, look at the state of the system, especially an equilibrium state, and the system itself may define a natural flow. In other words, time is not imposed like a ruler placed on a table. It may arise from the way the system is physically arranged, from its statistical condition, from the thermal information contained in it. This is why temperature becomes so important. Temperature is not merely how hot something feels. In physics, it is tied to how energy is distributed among microscopic possibilities. A hot object has energy spread among many internal motions and states. A colder object has a different distribution. Temperature is a compact way of describing a huge hidden arrangement. And in the thermal time view, that hidden arrangement may help define the system's own sense of flow. This does not mean every warm object literally invents a private fantasy of time. It means that in deep theories where time is not already sitting in the background, thermodynamics may provide the missing direction or rhythm by which change can be described. Think of it this way. If you entered a sealed world with no clocks, no sunrise, no outside signals, but you could observe how its internal state is thermally organized, perhaps that organization would tell you what its natural time is. Not time as a number on a wristwatch, but time as the flow under which the system looks like it is in equilibrium. This is subtle because equilibrium usually sounds still. If a system is in thermal equilibrium, you might imagine nothing interesting is happening. But equilibrium does not mean the microscopic world is frozen. It means the large-scale statistical pattern is stable. Beneath that stability, there can be constant microscopic motion, exchange, fluctuation, and hidden structure. The thermal time proposal says that this stable statistical condition can define a special flow through the system's observables. It is as if the system's temperature does not merely sit inside time, but helps reveal which transformations count as its time evolution. Later work has discussed how thermal time can relate to geometric time in space-time, and how temperature can appear as a ratio between thermal flow and proper time in special cases, showing why the idea matters for connecting thermodynamics, relativity, and quantum theory. This is not a finished answer to the problem of time. It is a serious hypothesis, not a proven final law. Some philosophers and physicists have raised concerns that thermal time may still secretly rely on some notion of dynamics to get started, which means the idea must be handled with care. But even as a proposal, it changes the way you imagine reality. It tells you that time may not always be the invisible container in which heat moves. Sometimes, heat and statistical state may be part of how time is identified at all. This is especially fascinating near gravity, because gravity changes how time and temperature are experienced. In relativity, a clock near a massive object does not tick like a clock far away. In thermodynamics, systems in equilibrium can have temperature relationships that depend on gravity. These facts suggest that time, heat, and gravity are not separate islands. They touch. They bend into one another. A black hole makes this connection feel unavoidable, because black holes have temperature, entropy, horizons, and time distortion all woven together. The thermal time idea belongs to this deeper family of questions. Why do temperature, information, gravity, and time keep meeting at the edges of physics? Why does the flow of time seem connected not just to motion, but to what can be known, what is hidden, and how energy is statistically arranged? And here the concept becomes quietly personal, without becoming false. Your body also knows time partly through temperature and energy. A fever changes the speed of your thoughts. Cold slows your fingers. Warmth relaxes the nervous system. Exhaustion stretches minutes. Hunger sharpens them. Human experience is not the same as the thermal time hypothesis, but it reminds you that time has never been only a number. It is felt through physical state. Your sense of duration is tied to metabolism, attention, heat, chemistry, and the body's internal rhythms. Physics goes much deeper, of course, but the echo is real. Flow is never completely detached from condition. A frozen world and a burning world do not merely contain different events. They invite different ways of measuring and experiencing change. So when you hear that thermal time links temperature and flow, do not imagine a simple claim that hotter things have more time or colder things have less. Imagine something more careful and more profound. In a universe where no external clock may exist at the deepest level, the thermal state of a system might help define its own natural time. Temperature becomes not just a reading, but a clue. Heat becomes not just motion, but a map of hidden possibilities. And time becomes less like a command from outside reality, and more like a flow rising from within the physical state of the world itself. Perhaps the universe does not first receive time and then become warm. Perhaps, in some deep and still unfinished way, the warmth, the statistics, the hidden information, and the flow are part of one mystery, and every ticking clock is only the visible surface of that deeper thermal order. Some quantum histories can be combined consistently. A quantum event may not have one story waiting behind it, but under the right conditions, several possible stories can be arranged so carefully that they stop contradicting one another and begin to behave like a real history. This is the strange promise behind the idea of consistent quantum histories, a way of thinking about quantum mechanics that does not begin by asking, what did the particles secretly do when no one was looking? But instead, asks a more disciplined question. Which possible sequences of events can be assigned probabilities without destroying the logic of the theory? In ordinary life, a history is simple. You wake up, you cross a room, you open a door, you step outside. Even if no one watched you do it, the story feels complete. You assume there was a definite sequence linking one moment to the next. Classical reality is built from this confidence. A planet follows an orbit, a raindrop falls through air, a letter travels from one city to another. The details may be unknown, but the path feels definite. Quantum physics does not always grant that comfort. When a system is small enough and isolated enough, possible alternatives can overlap and interfere, which means you cannot always talk about them as if they were separate ordinary routes. One possible story can cancel or reshape another. The alternatives are not like independent roads on a map. They can behave more like waves crossing in water, where the pattern you see depends on how the waves combine. This is why careless storytelling becomes dangerous in quantum physics. If you say, the particle definitely went through this path, while the experiment still preserves interference between paths, you may be smuggling classical certainty into a situation where it does not belong. The consistent histories approach, developed in different forms by physicists such as Robert Griffiths, Roland Omnes, Murray Gell-Mann, and James Hartley, tries to avoid that mistake. It does not demand that every possible question about the past has an answer at the same time. Instead, it builds sets of possible histories, where each history is a sequence of physical alternatives at different moments, and then asks whether the set is consistent enough for ordinary probability rules to apply. If the histories within a set do not interfere with one another in the relevant way, then they can be treated like genuine alternatives. This history happened with some probability. That history happened with another probability, and the probabilities can be added and reasoned about without contradiction. But if the histories still interfere strongly, then trying to assign them classical probabilities is like trying to count shadows as separate objects while they are still merging on the wall. The framework refuses to let you create a false past just because your mind wants one. This is what makes the idea so quietly powerful. It does not say that quantum reality is meaningless. It says meaning must be built inside a consistent framework. You can ask certain historical questions, but not all questions can be combined into one single master story. In one consistent family of histories, it may make sense to describe a quantum system as having one kind of sequence. In another family, it may make sense to describe it in a different, incompatible way. The mistake is to take pieces from different families and force them into the same narrative as if they all belong together. This is sometimes called the single framework rule. Reason within one consistent set. Do not mix incompatible descriptions. That may feel strange because in daily life you expect all true facts to fit into one enormous encyclopedia. If a car was red and it was moving north and it passed a certain street at noon, all those facts can be placed into one story. But quantum physics can place limits on that kind of combination. Some descriptions are individually meaningful, but not jointly meaningful. It is not that nature is confused. It is that the questions carve reality in different ways. One framework may be useful for asking about position-like alternatives. Another may be useful for asking about momentum-like alternatives. But demanding both with classical sharpness can create a story no experiment supports. This is where consistent histories teaches a deep lesson about knowledge itself. A history is not merely a pile of imagined events. It is a structure that must obey the rules of what can be meaningfully known and predicted. In the quantum world, not every narrative your brain can picture is a valid physical account. Some stories are too fine-grained, too demanding, too eager to assign definite steps where the theory only permits combined possibilities. Other stories are coarse enough, stable enough, and separated enough from interference that they become usable. This is why the classical world can often be described through histories. Large objects interact with their surroundings in ways that make many alternatives effectively separate. So probabilities can be assigned and ordinary stories become reliable. A falling book, a moving car, a growing tree, a detector recording a signal. These are systems where the relevant histories are usually consistent enough that you do not need to worry about impossible combinations. But at the quantum level, the right to tell a story has to be earned. The alternatives must stop interfering before they can become chapters in the same book. This does not mean the universe waits for humans to narrate it. It means the structure of physical interaction determines which histories can be treated as real alternatives for explanation. A measuring device, an environment, a record, or a loss of interference can all help create conditions where consistent histories emerge. The result is a view of quantum mechanics that tries to speak about closed systems, even the universe as a whole, without always relying on an external observer standing outside the experiment. That matters because if you are describing the whole universe, there is no outside laboratory and no external witness. The histories must be internal to the universe's own physical structure. In this way, consistent histories offers a possible language for cosmology, where the universe's past is not imagined as a single classical film from the beginning, but as a set of possible quantum histories, some of which can be combined into meaningful probability assignments. And this is where the idea becomes gently unsettling. You are used to thinking that the past is one thing, solid and complete, whether you know it or not. But consistent histories suggest that at the quantum level, the past may be something you have to describe with care. The facts available depend on the framework of questions that can be consistently asked. This does not make truth disappear. It makes truth more disciplined. It says that reality is not obligated to satisfy every kind of curiosity at once. You cannot always demand a full classical biography from a quantum system. Sometimes you can only ask a family of compatible questions and accept the history that belongs to that family. That may feel limiting, but it is also freeing because it protects you from false certainty. It teaches that a clear story is valuable only when the world has physically earned the right to have one. And perhaps this is why the idea has a soft human echo, even though the physics itself is precise. In life too, you often try to combine incompatible stories about yourself. One memory says you were brave, another says you were afraid, one version says a choice was a mistake, another says it made you who you are. You want one final narrative that holds every angle without tension. But sometimes different descriptions belong to different ways of asking. Human life is not a quantum calculation, and we should not pretend it is. Yet the lesson of consistent histories still invites humility. Not every true perspective can be carelessly merged into one simple story. Some accounts make sense only within the context that gives them meaning. Some paths become coherent only when the right questions are asked together. So when you hear that some quantum histories can be combined consistently, imagine a universe that does not hand you one easy plot, but does offer islands of lawful storytelling inside a sea of possibility. Imagine histories forming not because the mind demands them, but because interference has quieted enough for alternatives to stand apart. Imagine truth not as a single flat timeline, but as a careful architecture of compatible questions. And maybe that is the deeper beauty of the idea. Quantum physics does not forbid history, but it asks history to become honest. It asks every story to prove it belongs with the others before it claims to describe what happened. Indefinite causal order breaks, before and after logic. Before and after feel so basic that they seem impossible to break. Yet quantum physics has found situations where the order of events may not be fixed in the ordinary way at all. Your mind depends on sequence. You press a key, then a letter appears. Lightning flashes, then thunder arrives. A question is asked, then an answer follows. This before and after logic is so deeply woven into experience that it feels less like an idea and more like the skeleton of reality. Even when events are confusing, you still assume there is a true order underneath them. A hidden timeline where everything happened one step at a time. But indefinite causal order challenges that assumption in a very precise way. It asks whether, in certain quantum processes, two operations can occur without the universe committing to a single definite order between them. Not simply because we do not know the order, Not because our instruments are too weak, and not because the events are too fast to track, but because the physical process itself may not be describable as only A before B, or only B before A. This is a different kind of uncertainty from losing the timeline in a messy situation. If two people speak at once in a noisy room, you may not know who started first, but there was still a fact of the matter. Someone's voice began slightly earlier, even if you missed it. Indefinite causal order is stranger. It suggests that under certain quantum conditions, the order can be in a kind of superposed structure, where the process cannot be reduced to one ordinary sequence without losing what makes the experiment work. In the classical world, events are arranged like sentences in a book. You can shuffle your memory of them, misunderstand them, or forget them, but the printed order remains. In the quantum world, at least in the language of quantum information, the order itself can become part of what is being controlled, combined, or left undefined. This does not mean people can create paradoxes, kill their grandparents, or send messages freely into the past. It does not mean causality has collapsed into fantasy. The science is more careful and more fascinating than that. Indefinite causal order does not destroy the need for consistency. It breaks the assumption that every allowed physical process must fit neatly into one background sequence of operations. To understand it gently, imagine two laboratories, each performing a different operation on a quantum system. In ordinary thinking, the system must visit one lab first and the other second. Maybe it goes through Alice's lab, then Bob's. Or maybe it goes through Bob's lab, then Alice's. Those are the two classical possibilities. If you do not know which happened, you might assign probabilities. Perhaps Alice first with some chance, Bob first with another. But that is still a mixture of definite orders. It is like saying a letter took one of two routes through a city, even if you do not know which route. Indefinite causal order asks for something deeper. What if the process is not merely a random choice between routes, but a quantum combination of orderings? What if the structure that decides the order is itself quantum, so the system is not simply traveling through one timeline or another, but through a process where which operation came first is not a settled classical fact? The best-known example connected to this idea is the quantum switch, where the order of two operations can depend on the state of a control system. If the control is in one condition, operation A happens before B. If it is in another condition, B happens before A. But if the control is placed in a quantum superposition, then the order of A and B can become indefinite in a meaningful operational sense. The process can produce advantages in communication and computation tasks that no simple fixed order arrangement can match as efficiently. That is important because physics is not just telling a strange story. It is giving scientists a way to test whether indefinite order has practical consequences. If the effect helps perform certain information processing tasks, then it is not just poetic language. It is a physical resource, something that can be used. And yet, this must be said carefully. These experiments do not prove that everyday time is broken, or that macroscopic events around you are floating without order. They show that quantum operations can be arranged in ways where the causal order is not classically definite, and that such arrangements can be described, controlled, and sometimes exploited. The deeper question, whether space-time itself, especially in quantum gravity, may have indefinite causal structure at a fundamental level, remains open, but it is one of the reasons this topic matters so much. In general relativity, gravity is tied to the shape of space-time, and the order of events can depend on that structure. In quantum theory, physical systems can exist in superpositions. So if gravity and space-time themselves eventually need a quantum description, then perhaps the causal order of events may not always be fixed in advance. Maybe the geometry that tells one event whether it is before, after, or unreachable from another could itself become uncertain. This is speculative at the frontier, not settled fact, but it is a serious line of thought. It invites a vision of the early universe, black holes, and the smallest scales of reality where the neat background stage of time may no longer be stable enough to define one universal order. What makes indefinite causal order so powerful is that it does not merely add another weird quantum trick. It reaches into the grammar of explanation. Most explanations begin with sequence. First this happened, therefore that happened. But if the order is not always definite, then explanation must become less like a chain and more like a structure. Instead of asking only, which event came first? Physics may sometimes ask, what whole process connects these operations and what correlations does it allow? This is a more abstract way of thinking, but it can also be clearer. It stops forcing the quantum world to imitate the storytelling habits of human memory. It allows nature to organize influence in ways that are consistent, testable, and lawful, even when they do not resemble a row of falling dominoes. And maybe that is why the idea feels quietly unsettling. Before and after logic is not just a scientific tool, it is how you protect meaning. You apologize because something you did caused harm. You prepare because something you do now may shape what comes later. You trust reality because actions appear to have consequences in order. Indefinite causal order does not erase that human world. It does not make responsibility meaningless or daily life unstable. But it does reveal that the familiar order you live by may be an emergent, large-scale clarity rather than the only possible architecture of events. At small enough scales, in carefully arranged quantum processes, the universe can be lawful without being sequential in the way your intuition expects. It can preserve consistency while loosening the timeline. It can let A before B and B before A stop being rival stories and become ingredients of one deeper process. So when you hear that indefinite causal order breaks before and after logic, do not imagine time collapsing into nonsense. Imagine something more disciplined and more mysterious. A reality where order itself can become quantum, where the route through events is not always a fixed road, where causality remains real but may not always wear the simple shape of a line. And perhaps the deepest lesson is this: the universe may not be built from stories first. Stories may appear only after reality has become classical enough for events to stand in a clear row. Beneath that row, there may be a quieter grammar, one where before and after are not destroyed, but gently released from being the only way nature is allowed to make sense. The quantum switch makes event order unclear. A quantum switch is like sending a message through two sealed rooms, only to discover that nature has not clearly decided which room the message entered first. In ordinary life, order feels unavoidable. You put a key into a lock before the door opens. You read the first page before the last page makes sense. You walk through one room, then another, and even if you forget the sequence, the world itself still seems to know. But the quantum switch is a real scientific idea that makes this confidence tremble in a very precise way. It does not say that everyday events become chaotic, or that your breakfast can happen before you wake up, or that time has collapsed into nonsense. It says something subtler and more fascinating. In a carefully designed quantum process, two operations can be applied to a system in an order that is not simply first A, then B, or first B, then A, but in a coherent quantum combination of both possibilities. The order itself becomes part of the quantum structure. To imagine it, picture a photon traveling through an experimental setup. The photon has some property that can act like a control, such as its polarization or path. If the control is in one condition, the photon experiences operation A before operation B. If the control is in another condition, it experiences B before A. But quantum physics allows the control to be placed in a superposition, not just one condition or the other. Then the process is no longer just a hidden coin toss between two definite orders. It is not that the photon secretly took one sequence while the scientist failed to notice. The whole point is that the two possible orders can remain coherently connected, like two routes that are not merely alternatives, but part of one deeper quantum arrangement. This is why the word switch is so powerful. It sounds mechanical, like a button selecting a route. But at the quantum level, the switch itself can be undecided in a controlled way. It does not choose one order in the classical sense. It lets order behave quantum mechanically. Experiments with photonic quantum switches have tested this idea by arranging operations so that the causal order cannot be explained as a simple definite sequence, and one well-known experiment used a causal witness, similar in spirit to how entanglement can be certified, to show evidence beyond a definite order bound. That detail matters because this is not only a philosophical image. Scientists do not just announce that order is unclear because the idea sounds beautiful. They build physical tests, compare the results against what would be possible if the order were definite, and ask whether the data crosses that boundary. In another experimental direction, researchers have shown that quantum switching can provide advantages in certain communication and computation tasks, because applying operations in a superposition of orders can sometimes use information more efficiently than any fixed order strategy. This is where the quantum switch becomes more than a strange toy. It suggests that causal order itself can be a resource, something nature can use in information processing. Usually, when you think of a resource in physics, you imagine energy, charge, mass, or maybe entanglement. But the quantum switch hints that the order of operations, when made quantum, can also have power. It can help reveal properties of unknown operations, reduce the number of times something must be used, or create advantages in specially designed tasks. That does not mean quantum switches will let ordinary computers magically solve every problem. And it does not mean the effect is easy to scale into everyday technology. The experiments are delicate, the interpretation must be careful, and physicists still discuss how far laboratory versions of indefinite order should be taken when compared with truly indefinite spacetime structure. Some researchers emphasize that optical quantum switches demonstrate indefinite order of operations in a controlled quantum information setting, while deeper questions about spacetime itself may require quantum gravity, where the geometry determining causal order could itself be uncertain. This distinction keeps the wonder honest. A quantum switch is not a portal into time travel. It is a precise way of showing that the sequence of two operations can fail to have a single classical order. That alone is already astonishing. It means that before and after, at least for certain quantum operations, may not be the fixed background labels you instinctively imagine. They can become part of the experiment's internal quantum logic. If you open the box too early, the ordinary world returns. One root, one order, one record. But while the system remains coherent, the two orders can work together. They can interfere, carry information, and produce results that cannot be reduced to a simple story of one operation definitely happening before the other. This forces you to rethink what an event sequence really is. In classical thinking, the order is like a railroad track, and the system is a train moving along it. In the quantum switch, the track itself becomes conditional, flexible, and partly quantum. The train does not merely choose left or right. The railway of sequence is placed into a controlled ambiguity. And yet the ambiguity is not disorder. It is not confusion. It is structured enough to be tested, useful enough to create advantages, and fragile enough to vanish if the environment learns too much. That fragility is important because it explains why you never notice quantum switches in ordinary life. The world around you is flooded with records. Light scatters, air interacts, surfaces absorb, memories form. Large events become locked into sequences quickly. Your hand touches the cup before the cup moves. The sound reaches you after the impact. The message is sent before it is received. These orders are stable because the environment keeps writing them down. But in a controlled quantum experiment, before the order becomes publicly recorded, nature can keep something deeper open. The sequence can remain coherent. The two possible orders can be held together just long enough for their combined effect to matter. This is the part that should make a listener pause. The quantum switch does not break reality. It reveals that the reality we call normal may be a simplified surface built from countless fixed records. Beneath that surface, even the order of operations can become something more flexible than common sense allows. And perhaps this is why the idea feels so quietly haunting. Your life is made of sequence. First meetings, last words, decisions before consequences, causes before regrets. You understand yourself through order. But quantum physics shows that order is not always the most basic thing. Sometimes order is something that becomes definite only under the right physical conditions. Sometimes before and after are not the starting point of explanation, but part of what the experiment is allowed to place into question. So when you think of the quantum switch, do not imagine a clock spinning wildly or a timeline shattering into fantasy. Imagine a delicate laboratory arrangement where two possible orders are held, like two notes in the same chord, neither alone, neither fully chosen, both contributing to the final sound. The result is not chaos, it is a deeper grammar. It tells you that causality may have layers, the rigid order of daily life above, and beneath it, a quieter quantum level, where even the path through events can become a physical possibility rather than a fixed command. And in that small controlled switch, you glimpse a larger mystery. Perhaps the universe becomes a story only after its deeper processes have agreed on the order in which the pages can be read. Retrocausal interpretations treat future conditions seriously. The future is usually treated like an empty room waiting for you to enter, but some serious interpretations of quantum physics ask whether that room may already help shape the hallway behind you. This does not mean the future sends messages backward like a science fiction signal, and it does not mean your tomorrow can magically rewrite your yesterday in any useful or controllable way. Retrocausal interpretations are much more careful than that. They begin with a real problem in quantum physics. When tiny systems are measured, the outcomes are connected to the measurement setup in ways that resist ordinary explanation. In many experiments, it looks as if a quantum system does not carry a complete set of fixed properties before measurement. Yet when a measurement is chosen, the result fits the whole experimental arrangement with astonishing precision. The usual way to speak about this is to say the past prepares the system evolves, and the later measurement reveals or helps produce an outcome. Retrocausal interpretations ask whether that one-way picture is too narrow. They treat both the earlier preparation and the later measurement as important boundary conditions, almost like two ends of a bridge. Instead of saying the past alone pushes the quantum system forward until the future passively receives the result, they ask whether the full quantum event may be best understood by considering both what came before and what will be measured later. This is not the same as breaking causality. It is more like saying that the complete explanation of a quantum process may require information from both ends of the experiment. In ordinary life, this feels wrong, because you are used to causes coming first and effects coming after. But physics has many cases where a whole system is understood through boundaries. A guitar string's final sound depends not only on one tiny piece of the string, but on how the whole string is fixed at both ends. A path through a landscape can be described by its starting point and destination, even though you experience the walking step by step. A shadow's shape depends on both the object and the surface where it falls. Retrocausal thinking uses a similar spirit, but in a much deeper quantum setting. Perhaps the properties between preparation and measurement are not fully determined by the beginning alone, but by a combination of beginning and end. This idea becomes especially tempting when physicists think about quantum entanglement and Bell-type experiments, where measurements on separated particles show correlations stronger than any simple local hidden variable model can explain. The standard lesson is that nature cannot be described by ordinary local properties that exist independently of how they are measured. Some interpretations accept non-locality, meaning the description of one particle seems inseparable from the measurement context of another far away. Retrocausal approaches explore another route. Maybe the hidden description can remain local in a certain sense if later measurement settings are allowed to act as boundary conditions, reaching backward along the particle's own history. Again, this does not allow you to send a usable message into the past, because the outcomes remain probabilistic and cannot be controlled in the way communication would require. No one can choose tomorrow's measurement and use it to warn yesterday. The theory must still protect the ordinary rule that signals cannot be sent backward to create paradoxes. But it may allow the mathematical description of a quantum event to depend on future conditions in a way that ordinary intuition finds uncomfortable. The discomfort comes from the fact that your mind confuses influenced by the future with controlled by the future. Retrocausal. Interpretations do not need the future to behave like a person reaching into the past and changing a decision. They can treat the quantum event more like a four-dimensional pattern, where the whole arrangement across time must fit together consistently. From inside time, you experience the pattern one moment after another. From the viewpoint of the theory, the full event may be constrained from both temporal sides. This is why retrocausality can sound mystical when described carelessly, but becomes more sober when described as a boundary condition idea. It is not saying your future self is secretly pulling strings. It is saying quantum reality may not always be best explained as a tiny object carrying definite instructions from the past alone. Some models, such as the transactional interpretation or two-state vector approaches, take future measurement conditions seriously by describing quantum processes with both forward-moving and backward-related elements. These are interpretations, not universally accepted facts, and physicists do not all agree on what they imply. But their value is that they force a difficult question into the open. Why should explanation in quantum physics be allowed to use only the past? If the formal structure of the theory often connects preparation and measurement so tightly, in classical life, the past feels privileged because it is recorded. You remember it. You can photograph it, write it down, leave traces of it. The future has no records for you yet. So it feels natural to say the past is real and active, while the future is unreal and passive. But a law of physics does not have to feel time the way a human nervous system does. A complete physical pattern may not care about your psychological access. It may treat what you call later as part of the condition that gives the whole event its shape. The challenge is to say this without lying. Retrocausal interpretations do not prove fate. They do not prove that your choices are already written in a simple way. They do not prove that consciousness bends time. They do not prove time travel. What they offer is a possible way to understand quantum weirdness without assuming that the only acceptable influence must run from past to future in the ordinary classical sense. They invite a universe where consistency may be deeper than sequence, where a quantum event is not simply pushed forward like a ball rolling downhill, but fitted into a larger structure that includes how it begins and how it is finally examined. This can also clarify why retrocausality does not create obvious paradoxes. In a paradox, you imagine changing the past in a way that prevents the future condition that caused the change. But most retrocausal models do not allow free, visible rewriting. They allow only self-consistent correlations. The past and future conditions must fit together as one lawful pattern. You cannot use them as a weapon against the timeline, because the outcomes are not under your command in that way. The future condition is serious, but not obedient. It helps constrain the event, but it does not become a telephone line to yesterday. This is the quiet beauty of the idea. It asks you to loosen the grip of everyday storytelling without abandoning evidence. It says the quantum world may not be a chain of little facts marching forward, but a delicate agreement between what is prepared, what is measured, and what can exist consistently between them. And perhaps this is why retrocausal interpretations feel so haunting. They do not simply make physics strange. They make responsibility, memory, and possibility feel different. You are used to thinking that only the past gives meaning to the present. But in life, even without invoking quantum mechanics, the future often changes the meaning of what came before. A failure becomes training only after growth arrives. A painful goodbye becomes mercy only after another life opens. A quiet decision becomes important only when its consequences unfold years later. This is not proof of retrocausality in human life, but it helps your mind approach the scientific idea. Sometimes the meaning of a middle moment depends on both ends of a story. Quantum retrocausal interpretations take that kind of two-ended seriousness into the foundations of measurement itself. They ask whether the universe, at its smallest scales, may be less like a sentence written left to right, and more like a poem whose final line changes how every earlier line must be understood. So when you hear that retrocausal interpretations treat future conditions seriously, do not imagine fantasy, prophecy, or a broken timeline. Imagine a disciplined attempt to make sense of quantum experiments by allowing the end of the experiment to matter as deeply as the beginning. Imagine reality not as a loose sequence of isolated instants, but as a self-consistent structure stretched across time, where what comes later cannot be ignored when explaining what was possible before. And maybe the softest lesson is this: the future may not be a ghost controlling the past, but in quantum physics, it may not be completely silent either. It may be one side of the frame that lets the whole picture hold together. Two-state vector formalism uses past and future boundaries. A quantum system can be described as if it is being held between two hands at once. One hand reaching from the past that prepared it, and another reaching from the future that finally measured it. This is the quiet, unsettling idea behind the two-state vector formalism, a way of writing quantum mechanics that takes both ends of an experiment seriously. In the ordinary picture, you usually imagine a quantum system beginning in some prepared condition, then evolving forward until a measurement happens. The story feels familiar. First the setup, then the journey, then the result. Even if the system behaves strangely along the way, the direction of explanation still feels mostly one way. The past sends the system forward. The future receives whatever outcome appears. But the two-state vector formalism, developed by Yakir Aharonov and collaborators, asks you to look at the middle of a quantum experiment differently. It says that if you know not only how a system was prepared at the beginning, but also which result was found at the end, then the most complete description of the system in between can use two pieces of information. One evolving forward from the initial preparation, and one evolving backward from the final measurement. This does not mean a future scientist is changing the past with intention. It does not mean time travel. It does not mean you can decide an outcome tomorrow and send a message into yesterday. It means that when physicists describe a system that has both a known starting condition and a known ending condition, the mathematics can treat the interval between them as constrained by both boundaries. The system is not explained only by where it came from, but also by how it is later found. Think of a river between two fixed shores. If you only know the source, you can predict many possible ways the water might spread. If you also know the exact shape of the place where the river must arrive, the middle becomes more tightly constrained. The river is not being magically pulled backward in a childish sense, but the full description of its path depends on both ends. In quantum physics, this becomes far more subtle because the path is not usually a definite classical route. The formalism gives you a way to ask, given that the system began like this and was later detected like that, what can meaningfully be said about it in the time between? The answer can be strange, because quantum systems do not always behave as if they carried a simple list of properties from preparation to measurement. A particle may be prepared in one state, later selected by a particular final result, and in the middle its description may carry information from both directions. This is why the formalism is often called time-symmetric. It does not deny that experiments happen in a sequence for us. The laboratory still prepares first and measures later. The notebook still records results after the fact, but the underlying description of the quantum system can be written in a way that is more balanced between past and future than everyday intuition expects. The key idea is called pre-selection and post-selection. Pre-selection means the system is prepared in a known initial condition. Post-selection means that after the experiment, you keep only the cases where a specific final result occurred. By focusing on those selected cases, physicists can study the system between the two boundary conditions. This is not cheating. It is like studying only the arrows that began from one point and ended in one target, then asking what can be inferred about the flight between. In classical physics, this would usually just narrow down a normal path. In quantum physics, it can reveal patterns that feel almost impossible if you insist on only a forward-moving story. The middle state is described by two vectors, one from the past and one from the future, and together they shape the probabilities of what could be observed during the interval. You do not need heavy symbols to feel the strangeness of this. Imagine watching a sealed box. You know exactly how something was placed inside it. Later, you open the box and find a very specific result. Now you ask, what was true inside the box between those two moments? In daily life, you assume there was one hidden sequence of facts. But quantum physics warns that this assumption can fail. The two-state vector formalism offers a controlled language for that failure. It says, the in-between reality may be best described not as a single hidden classical story, but as a quantum condition, shaped by both the first preparation and the last measurement. It is as if the middle of the experiment is not a lonely moment drifting away from its origin, but a meeting place between two constraints. The past says, it began this way. The future says, it ended this way. And the quantum description in between must respect both. This is why the formalism is closely connected to some of the strangest discussions in quantum foundations, including weak measurements, delayed choice-style reasoning, and questions about whether quantum properties can be meaningfully discussed between ordinary measurements. But it is important not to exaggerate. The two-state vector formalism is not universally accepted as the final meaning of quantum mechanics. Many physicists treat it as an alternative formulation, a powerful and sometimes illuminating way to calculate and interpret pre-selected and post-selected quantum systems. It is compatible with standard quantum predictions when used properly. Its boldness lies not in producing a different universe of experimental results, but in changing the way you think about what the quantum state is telling you. In the usual view, the quantum state often feels like a wave of possibility moving forward from the past. In this view, during the interval between preparation and final measurement, the system is described by a pair, the forward evolving state from the beginning and the backward evolving state from the end. The middle is not explained by one direction alone. That change in perspective is enough to make time feel less like a simple corridor and more like a room with two doors. You enter from one side, yes, but the shape of the room also depends on where you leave. What makes this especially fascinating is that it gives the future a formal role without giving it magical control. The final measurement matters in the description, but it cannot be used to send chosen information backward. You cannot force a future result and then use it to alter the past, because quantum outcomes are still governed by probability, and the post-selection is only known after the experiment is completed. You can sort the successful cases afterward, but you cannot use that sorting to build a paradox. This keeps the idea grounded. It lets the future boundary be serious without turning it into fantasy. And that is where the beauty lives. The two-state vector formalism does not say the universe is a puppet show controlled from tomorrow. It says that in certain quantum descriptions, the complete information about a system between two measurements may come from both temporal edges. The future is not a voice commanding the past. It is a boundary condition helping define the whole pattern. If ordinary causality is like reading a sentence from left to right, this formalism asks whether a quantum sentence might sometimes be understood only when you also know its final word. The meaning of the middle is sharpened by the ending, not because the ending travels backward as a message, but because the full physical description is conditioned on both. This can feel deeply alien because human consciousness is built from memory, and memory points backward. You know the beginning before you know the end. You suffer through uncertainty before the result arrives. You experience life as unfinished while you are inside it. But physics, when it describes an experiment after both preparation and measurement are known, is allowed to use the whole structure. It can say, if these are the two boundaries, then this is the best description of the interval. And perhaps this is why the idea feels almost philosophical even before it becomes technical. Many moments in life are not understandable from their beginnings alone. A meeting becomes important only because of what it later becomes. A choice looks small until its consequences reveal its shape. A painful chapter can seem meaningless until the ending gives it a different weight. This does not prove that human life is quantum in the same way, and we should not pretend it does. But it helps you feel the conceptual shift. Sometimes the middle cannot be fully understood from the start alone. Sometimes the end is part of what makes the middle intelligible. In quantum theory, The two-state vector formalism turns that intuition into a precise tool for selected systems. It asks you to imagine reality between measurements as something more delicate than a forward-marching chain of facts. It may be a suspended interval, held between what was prepared and what was later found, with both boundaries contributing to what can be meaningfully said. So when you hear that this formalism uses past and future boundaries, do not imagine a broken timeline. Imagine a quantum event framed like a painting, with one edge fixed by preparation and the other by measurement. The image inside the frame does not belong to one edge alone. It belongs to the relation between them, and maybe that is the quiet shock. At the smallest scales, the universe may not always explain its present, only by pointing backward. Sometimes, to understand what a quantum system was between two moments, physics must let the future stand at the other side of the room, silent but real, helping shape the answer. Weak values can seem to point between times. A weak value is like a faint fingerprint left in the middle of a quantum event, visible only when you touch the system so gently that you almost learn nothing from any single touch at all. This is why weak values feel so strange. They seem to point into the hidden interval between preparation and final measurement, not with the certainty of a photograph, but with the softness of a trace. In ordinary measurement, you usually imagine a scientist asking a system a clear question and receiving a clear answer. If you measure a property strongly, the system is disturbed, the result becomes definite, and whatever delicate quantum possibilities existed before are usually destroyed or forced into one recorded outcome. A strong measurement is like switching on a bright light in a dark room. You see something clearly, but the room is no longer the same as it was in darkness. A weak measurement works differently. It couples so lightly to the quantum system that the disturbance is very small. The price is that one weak measurement tells you almost nothing reliable. The pointer barely shifts. The signal is buried in noise. If you tried to understand a single particle from one weak reading, you would be fooled by randomness. But if you repeat the same preparation many times, perform the same gentle measurement, and then keep only the cases where a chosen final measurement succeeds, a pattern can slowly emerge. That pattern is called a weak value, originally introduced in the famous Aharonov, Albert, and Weidmann framework, where a weak measurement combined with post-selection can produce results that look deeply counterintuitive, sometimes even lying outside the normal range of values expected from a strong measurement. This is the part that hooks the mind. A spin component that normally gives only certain allowed outcomes can produce a weak value that seems far beyond them. A particle can appear, through weak measurement language, as if it left traces in places that do not fit a simple path. A property can seem to take on an impossible intermediate value, not because the measuring device is broken, but because the weak value is not the same kind of thing as an ordinary measurement result. It is not a single revealed fact in the usual sense. It is a conditioned statistical quantity, extracted from an ensemble of systems that began in one known way and ended in another selected way. That distinction is essential if you want the science without the exaggeration. Weak values do not let you spy on a particle's secret life with perfect accuracy. They do not prove that a particle definitely had a bizarre property in the ordinary classical sense. They do not allow time travel, prophecy, or control over future outcomes. What they do is give physicists a mathematically precise way to describe what a very gentle intermediate probe reveals when both the initial preparation and the final post-selection are taken into account. In that sense, they seem to point between times. The weak value belongs to the interval after the system was prepared, but before its final result was known. And yet, it depends on both ends of the experiment. A single boundary from the past is not enough. The final selection matters too. The middle trace becomes meaningful only when the beginning and ending are considered together. This is why weak values are often discussed alongside time-symmetric approaches to quantum mechanics and pre-selected, post-selected systems, where the quantum system between two measurements can be described using information from both the first and second measurement conditions. To feel how strange this is without using heavy mathematics, think of trying to study a bird flying through fog. A strong measurement would be like throwing a net across the sky. You learn where the bird is, but you ruin its flight. A weak measurement is like placing extremely soft threads in the air. One thread bending tells you almost nothing. Wind, noise, and chance overwhelm the clue. But if the same flight is repeated again and again under the same conditions, and you later keep only the flights where the bird arrives at a particular window, the tiny bends in the threads may reveal a pattern about the kind of flight that connected that beginning and that ending. The pattern may not look like the path you expected. It may even seem to say the bird's presence was strangely distributed, but you must not confuse the pattern with a normal video recording. Weak values are not ordinary footage of the quantum past. They are more like a delicate average of almost undisturbed traces, filtered by a final condition. That is why they can feel both revealing and controversial. Some physicists treat weak values as offering insight into the reality of quantum systems between measurements. Others interpret them more cautiously, as useful statistical tools that summarize how weak probes behave under pre-selection and post-selection, without needing to claim that the system truly possessed the weak value as a normal property. This debate is not a weakness of the field. It is part of what makes it intellectually alive. The experiments are real, the pointer shifts are real, the predictions can be tested, but the meaning of those results is still discussed carefully, because quantum mechanics often gives reliable numbers before it gives intuitive pictures. A weak value can be useful in precision measurement because post-selection can amplify tiny shifts in a measuring device, making small effects easier to detect in some circumstances. Though this advantage has limits and must be evaluated honestly rather than treated as magic. The deeper lesson is that weakness can reveal what violence conceals. A strong measurement forces the system into a definite public answer, but it may destroy the subtle structure you wanted to study. A weak measurement preserves more of that structure, but gives only a whisper, and whispers require patience. You need many repetitions. You need careful filtering. You need humility about what the result means. That is why weak values sit in such a fascinating place between knowledge and disturbance. They show that asking softly can produce a different kind of information than asking loudly. Not more ordinary, not simpler, but more delicate. And because the weak value is shaped by the final post-selection, it can make the interval between past and future feel strangely illuminated from both sides. The system is prepared, then weakly touched, then finally measured, and only after the final outcome is known does the weak trace become sorted into a meaningful pattern. From your human point of view, this feels almost backwards. You want the middle to be explained by the beginning alone. But in weak value experiments, the middle statistic is conditioned on the ending too. The future result does not send a controllable message backward, but it helps define which ensemble you are studying. The ending changes the question you are allowed to ask about the middle. This is subtle, but it is not fantasy. It is one of the most careful ways quantum physics teaches you that what happened between may not be a simple hidden scene waiting to be uncovered. Sometimes the best you can get is a trace that becomes meaningful only when the full experimental frame is known. And perhaps this is why weak values feel so haunting. They do not smash time dramatically. They soften the walls between preparation, measurement, and interpretation. They suggest that the middle of a quantum event may carry information that is too fragile for a strong question, too strange for a classical story, and too dependent on context to be called a normal property. A weak value is not a loud answer, it is a conditional echo. It says, if the system began this way, and if it later ended that way, then a gentle probe in the middle would, across many trials, lean in this surprising direction. That is a very different kind of truth from the truth of a rock sitting on a table. It is not less scientific. It is more finely qualified. So when you hear that weak values can seem to point between times, do not imagine a particle leaving a clear diary of its journey, and do not imagine the future reaching back like a hand to rewrite the past. Imagine instead a nearly silent measurement, repeated again and again, its tiny pointer shifts, gathered only from the cases where the ending fits a chosen condition. Imagine the quantum middle not as an empty gap, but as a region where traces can exist without becoming ordinary facts, where the beginning and ending together shape what can be inferred. And maybe the softest lesson is this. In quantum physics, some truths cannot be shouted into existence. Some can only be approached lightly, patiently, almost like listening for footsteps in snow before the snow decides which path will remain. Quantum clocks change under gravity. A quantum clock does not simply sit inside gravity counting seconds. It becomes one of the most sensitive witnesses to the fact that gravity changes what a second means. You are used to thinking of gravity as a pull, a heaviness, the reason your feet stay on the ground and a dropped object falls instead of floating away. But in Einstein's view, gravity is not only a force-like experience, it is connected to the shape of space-time itself, and that means it changes the rate at which clocks tick. A clock closer to a massive body, deeper in a gravitational field, ticks slightly more slowly compared with a clock higher up, where gravity is weaker. This is called gravitational time dilation, and it is not a philosophical suggestion or a dramatic metaphor. It has been measured again and again with real clocks, and modern optical atomic clocks are now precise enough to detect the difference in ticking even across extremely small height differences. Gila researchers reported measuring gravitational time dilation across a separation of about 1 millimeter using an optical lattice clock, showing how sensitive today's atomic timekeeping has become. That fact should make the ground beneath you feel stranger. Your head is slightly farther from Earth's center than your feet. The top of a mountain is in a different gravitational condition than the sea below. A clock on a satellite does not keep time exactly like a clock on Earth. These differences are tiny in daily life, far too small for your body to notice directly, but they are real enough that precision technology must account for them. The deeper lesson is that time is not one universal substance poured equally over everything. Time is local. Time depends on the path a clock takes through space-time. And when the clock is quantum, made from atoms whose internal transitions define its ticking, this becomes even more fascinating. An atomic clock works because atoms have extremely regular energy transitions. Scientists use lasers or microwaves to compare a signal against those transitions, tuning the signal until it matches the atom's natural rhythm. Optical clocks use very high-frequency atomic transitions and have become some of the most precise measurement tools ever built, precise enough to support tests of relativity and future redefinitions of the second. But an atom is not outside gravity. It has mass, energy, position, motion, and quantum properties. So when you build a clock from quantum matter, gravity does not merely pull on the clock as a whole. It changes how the clock's passage of time compares with clocks elsewhere. Locally, the atom behaves normally. If you live beside the clock, you would not see it struggle to tick. A clock deep in gravity does not feel broken to itself. The difference appears when clocks in different gravitational conditions are compared. One clock's seconds are not identical to another's when viewed across gravitational height. That is the quiet shock. Each clock carries its own proper time, its own experience duration along its path. Gravity does not need to smash the clock to change its time. It only needs to curve the stage on which the clock exists. Now bring quantum physics into the picture more carefully. A quantum clock can, at least in principle and in some theoretical proposals, be placed into situations where its position or motion is not perfectly classical. If a clock's center of mass were placed in a quantum superposition of different heights in a gravitational field, then the clock could be associated with different rates of proper time along those different branches. Researchers have explored how gravitational time dilation for quantum clocks could appear in such conditions, and how it might connect internal clock states with motion or position, though this is a frontier topic and not a simple everyday effect. This is where the idea becomes beautifully uneasy. In classical relativity, you can say one clock is lower, one clock is higher, and they tick at slightly different rates relative to each other. In quantum theory, you may have to ask what happens if the clock is not simply here or there in the ordinary way. If its location is quantum delocalized, then the clock's internal ticking can become linked with its possible paths through gravity. Time dilation becomes not only a comparison between two ordinary clocks, but a feature that can interact with quantum possibility itself. This does not mean the clock experiences two conscious timelines, and it does not mean you can split yourself into magical versions with different ages. It means that when the physical system used as a clock has quantum degrees of freedom, the relation between time, position, gravity, and information becomes more delicate. The clock is no longer just a passive label maker. It is a physical participant whose internal rhythm can become correlated with where it is and how gravity affects it. In some theoretical discussions, this connection can lead to loss of visible quantum coherence, because different gravitational time rates can make different parts of a quantum state fall out of step with one another. Again, this must be said carefully. The broad idea is serious, but the exact size and observability of these effects depend on the system, the mass, the clock quality, and the experimental design. There is no need to exaggerate. The truth is already astonishing enough. A clock made from atoms can reveal that standing slightly higher or lower changes time. A quantum clock may help physicists probe how quantum theory and gravity fit together, because it sits precisely at the border where internal quantum evolution meets curved spacetime. And this border is one of the greatest unfinished regions in physics. Quantum theory describes matter and energy at small scales with extraordinary success. General relativity describes gravity and spacetime with extraordinary success. But bringing them fully together remains difficult. Clocks are central to that difficulty because time plays different roles in the two theories. In relativity, time is flexible and geometric. In quantum mechanics, time is often used as a parameter that tracks evolution. A quantum clock under gravity forces these ideas into the same room. It asks, what does it mean for a quantum system to keep time in a space-time that does not treat all clocks equally? What happens when the thing measuring time is itself subject to quantum uncertainty and gravitational redshift? How do internal atomic rhythms, motion, height, and curvature combine into one physical account? These are not questions from fantasy. They are questions precision physics is beginning to approach with real instruments. The emotional power of this is quiet but deep. You think of a second as something simple, a unit printed on a clock face, a small neutral container for events. But a second is not the same everywhere when gravity is involved. It is shaped by location, motion, and the geometry of the world. If you lift an atomic clock, you have not just moved an object through space. You have changed the way its time compares with the time below it. The difference is tiny, but it is a real crack in ordinary intuition. It means the universe does not own one master tempo. It is filled with local rhythms, each clock carrying its own thread through space-time. And when the clock is quantum, that thread may become sensitive to possibilities that ordinary clocks hide. So when you hear that quantum clocks change under gravity, do not picture gravity damaging the clock or time melting like wax. Picture an atom quietly ticking inside a curved universe. Its rhythm faithful to itself, yet different when compared with another rhythm elsewhere. Picture time not as a single drumbeat echoing through the cosmos, but as a collection of delicate local pulses, each shaped by the gravitational landscape it inhabits. And perhaps the most haunting thought is this: every moment you live is also local. Your body, your memories, your aging, your heartbeat, all unfold along your own path through space-time. You do not feel gravity changing time because you are carried with your clock. But the atoms know, the clocks know, and with enough precision, the universe confesses that even a small difference in height can become a difference in time, reminding you that time is not merely something you pass through, but something gravity quietly sculpts around you. Atomic timekeeping depends on quantum transitions. The most accurate clocks humans have ever built do not tick because gears move, but because atoms can change their internal energy in a way so consistent that civilization now trusts them to define a second. That may sound almost too small to be powerful. A clock based not on the swing of a pendulum, not on the turning of Earth, not on the motion of the sun across the sky, but on the hidden rhythm of quantum transitions inside matter. Yet this is exactly how modern atomic timekeeping works. For most of human history, time was taken from the sky. A day came from Earth's rotation, a year from Earth's orbit, and human life was organized around shadows, seasons, and celestial repetition. But Earth is not a perfect clock. Its rotation wobbles and slowly changes. Tides, earthquakes, atmospheric motion, and the shifting of mass inside the planet can slightly affect how it spins. The sky is beautiful, but it is not precise enough for the world we have built. Navigation, telecommunications, financial networks, satellites, physics experiments, and the internet all require time measured far more carefully than sunrise and sunset can provide. So science looked inward, away from the sky and into the atom, and found something extraordinary. Atoms of the same kind are identical in a way no handmade object can ever be. One cesium atom is not like a clock assembled in one factory, and another cesium atom made in a slightly different factory. It is the same kind of quantum system, governed by the same natural rules. If you can isolate it, control it, and ask it the right question, it will answer with a frequency that is astonishingly stable. Atomic clocks depend on quantum transitions, which means that atoms do not absorb or emit energy in any continuous casual amount they like. Their electrons and internal magnetic states can exist only in certain allowed energy arrangements. When an atom shifts between two such arrangements, the energy difference corresponds to a very specific frequency of radiation. That frequency becomes the rhythm. In a cesium atomic clock, the famous standard is based on a hyperfine transition in cesium-133, a tiny change connected to the interaction between the atom's nucleus and its outer electron. Scientists send microwave radiation towards cesium atoms and tune the radiation until it matches the transition exactly. When the microwaves are just right, the atoms respond most strongly. The clock then locks itself to that natural response. It is not counting little mechanical clicks. It is counting cycles of electromagnetic radiation matched to a quantum transition. A second is defined by counting a fixed number of those cycles. This is one of the most beautiful shifts in the history of measurement. Time is no longer defined by the imperfect turning of a planet, but by a repeatable quantum property of matter itself. And the deeper you look, the more elegant it becomes. An atomic clock is not simply an atom sitting in a box. It is a carefully engineered conversation between atoms, fields, lasers or microwaves, detectors, cooling systems, and feedback loops. The atoms provide the natural reference. The electronics provide the counting. The control system keeps everything tuned. If the applied radiation is slightly too high or too low in frequency, the atoms respond differently and the clock corrects itself. It is almost like listening for a perfectly pure note in a room full of noise, then adjusting your instrument until the note and the atom agree. The atom is not obeying the clock is obeying the atom. This is why atomic timekeeping is so powerful. The tick comes from a universal quantum transition, not from a human-made mechanism slowly wearing down. Modern optical atomic clocks go even further. Instead of using microwave transitions, they use optical transitions at much higher frequencies, meaning there are many more cycles per second to count. More cycles can allow finer divisions of time, like using a ruler with far smaller marks. These clocks may use atoms such as strontium, ytterbium, or aluminum ions, held in traps or optical lattices, cooled to extremely low temperatures, so their motion does not blur the measurement too much. Lasers probe the atoms with incredible stability, and the clock compares the laser's frequency to the atom's transition. If the laser drifts, the atom reveals the drift. The atomic transition becomes a quiet judge of precision. This is not only useful for telling time, it turns clocks into scientific instruments. Atomic clocks can test whether physical constants remain stable, help compare locations and motion, support satellite navigation, and probe the subtle behavior of nature with a sensitivity that would have seemed impossible not long ago. But the important idea for this journey is simpler and deeper. Quantum transitions make timekeeping possible because nature gives atoms discrete, reproducible changes. Without quantum rules, there would be no such sharply defined atomic reference. If atoms could absorb any energy at any amount with no stable internal structure, they would not provide the same clean rhythm. The clock depends on the fact that quantum systems have allowed states and forbidden in-betweens. Timekeeping, at its most precise, is built from nature's refusal to be continuous in the old classical sense. And there is something quietly humbling in that. You may experience time as flowing, soft, personal, emotional. A childhood summer that feels endless. A painful night that refuses to pass. A good hour that disappears too quickly. But beneath the technologies that coordinate the modern world, time is counted through transitions so tiny, no human sense can feel them. The meeting starts, the plane lands, the message sends, the satellite locates you, the network synchronizes. And beneath all of it, atoms are being asked the same question again and again. Are we tuned to your transition? Are we still aligned with your rhythm? The answer becomes civilization's pulse. Yet even atomic time is not a magical possession of time itself. It is a measurement, a disciplined comparison, an agreement between a physical system and a counting device. The atom does not tell us what time is in the final philosophical sense. It gives us a remarkably stable way to measure duration. That distinction matters. A clock does not capture time like a jar captures water. It marks change by comparing one regular process with others. Atomic clocks are extraordinary because the regular process is rooted in quantum structure. They turn the invisible architecture of the atom into the most reliable metronome humanity has found. So when you hear that atomic timekeeping depends on quantum transitions, imagine not a cold machine, but a hidden choir of atoms responding only to the exact note nature allows them to hear. Imagine time being measured not by the sky above you, but by the inner music of matter, by tiny shifts between allowed states, repeated with such faithfulness that the modern world can stand on them. And perhaps that is the soft wonder at the center of it. The second you treat as ordinary, the little unit you spend without thinking, is now anchored to one of the deepest facts of quantum reality, that atoms do not change in just any way, but in precise steps, and from those steps we build the rhythm of our days. The universe's first clock is still a mystery. The first clock in the universe may not have had hands, atoms, light, or even a stable meaning of before and after. And that is why the beginning of time is still one of physics' quietest mysteries. When you hear that the universe is about 13.8 billion years old, it sounds as if someone simply looked at a cosmic stopwatch and read the number. But there was no stopwatch at the beginning. There were no planets turning, no stars pulsing, no atoms changing energy levels, no crystals vibrating in a machine, no sunrise, no shadow, no observer standing outside the newborn cosmos saying, "Now the first second has passed." A clock is not just a device. A clock is any physical process regular enough to compare other processes against. Earth's rotation once served as a clock. Atomic transitions serve as our best clocks today. Pulsars can act like cosmic lighthouses. The expansion of the universe can serve as a kind of large-scale clock. But at the very beginning, the question becomes strange. What physical process was stable enough, separate enough, and meaningful enough to count time when the universe itself was unimaginably hot, dense, rapidly changing, and perhaps governed by physics we do not yet fully understand? In the standard picture of cosmology, scientists can speak about cosmic time after the universe becomes describable by general relativity and known particle physics. They can work backward from the expansion of space, the cosmic microwave background, the abundance of light elements, and the behavior of matter and radiation. The universe cools as it expands, and that cooling becomes a kind of clock. When the temperature was high enough, certain particles could exist freely. When it dropped, certain reactions stopped. When it cooled further, protons and neutrons formed nuclei. Much later, electrons joined nuclei to make neutral atoms, and light began traveling freely through space. In this sense, the early universe left behind milestones, not clocks with faces but physical thresholds. A certain temperature means a certain era. A certain density means a certain kind of interaction. A certain expansion rate tells us how quickly conditions were changing. The universe's first readable clock may have been its own cooling, its own expansion, its own transition from one physical state to another. But when you push the question all the way back, toward the earliest possible moments, the confidence begins to thin. Before atoms, there were no atomic clocks. Before stable nuclei, no nuclear structure like the matter around you today. Before light could travel freely, the universe was a glowing plasma where photons constantly scattered from charged particles, unable to cross space cleanly. Even the cosmic microwave background, often called the oldest light we can see, did not come from the absolute beginning. It comes from about 380,000 years after the hot Big Bang, when the universe finally became transparent. That ancient light is a magnificent fossil, but not the first tick. Earlier still, during the first minutes, nuclear reactions produced much of the hydrogen and helium that would later fill stars. That process, called Big Bang nucleosynthesis, gives another powerful time marker, because the amount of these elements depends on how the early universe expanded and cooled. But even that is not the first tick. Go back to the first fractions of a second, and the universe becomes a place where particle physics, radiation, and extreme energies dominate. Go back further still, toward the Planck era, and our current theories no longer fit together cleanly. General relativity tells us how space-time behaves on cosmic scales. Quantum physics tells us how matter and energy behave at tiny scales. But at the earliest times, when the entire observable universe was compressed into conditions where both gravity and quantum effects were extreme, we likely need a theory of quantum gravity, and we do not yet have a complete one. This is where the first clock becomes truly mysterious. If time itself is part of space-time, and space-time was in a quantum, unstable, or not yet classical condition, then what does it mean to ask what clock was ticking? A clock needs change, but change needs some notion of time. A clock needs distinguishable states, but in the earliest universe, the very difference between one state and the next may not have been expressible in the familiar way. It is possible that what we call cosmic time only becomes clearly meaningful after the universe enters a regime where space-time behaves classically enough for expansion to be described smoothly. Before that, asking what was the first clock may be like asking for the first wave on an ocean before water itself has settled into being water. This does not mean science knows nothing about the beginning. It means science is honest about the boundary between what can be reconstructed and what remains hidden. We can trace the universe back through evidence. The stretching of light from distant galaxies, the afterglow of the early hot plasma, the ratios of primordial elements, the large-scale structure of galaxies, and the tiny temperature patterns that grew into cosmic architecture. These are not guesses. They are physical clues, but clues become fewer and more indirect as we approach the earliest moments. The first clock might not have been a thing at all. It may have been the first reliable relationship between physical quantities, expansion compared with temperature, energy compared with density, particle interactions compared with the rate of cosmic stretching. In the early universe, reactions happened only if particles could find one another fast enough before expansion pulled conditions apart. That competition between interaction and expansion acted like a primitive timing system. If reactions were faster than expansion, matter stayed in balance. If expansion won, certain processes froze out, leaving permanent traces in the universe's composition. In that sense, the newborn cosmos may have counted time through races: particles against expansion, cooling against reaction, gravity against pressure, instability against smoothing. But still, something deeper waits beneath the language. Who or what defined the first before from which these races began? Did time begin sharply with the Big Bang? Or did our current description begin there while something deeper preceded it in a form we do not yet understand? Some models imagine a bounce before the hot expanding phase. Others imagine inflation, a very early burst of rapid expansion that may have stretched tiny quantum fluctuations into the seeds of galaxies. Others suggest that time near the beginning may not behave like the flowing time we know at all. None of these ideas should be treated as settled truth just because they sound fascinating. They are serious attempts to approach a place where evidence becomes difficult and theory becomes fragile. The honest mystery is not whether the universe changed. Clearly it did. The mystery is what allowed change to be measured at the very first edge of physics. A clock is meaningful only when there is enough structure to say one condition differs from another in an ordered way. Maybe that structure emerged gradually. Maybe the universe did not begin with a clock, but became clock-like as space-time, matter, radiation, and stable physical laws took on forms that could preserve sequence. And perhaps this is why the idea feels so haunting. You live surrounded by clocks so completely that time feels automatic. Your phone counts it. Your body ages through it. Your memories organize themselves around it. But the universe may have passed through a stage where no ordinary clock could exist, and maybe even where ordinary time itself was not yet fully formed. The first clock, if there was one, was not made by hands and did not mark seconds for anyone. It may have been the first pattern stable enough to make earlier and later meaningful. The first physical rhythm in a cosmos, still learning how to become a history. So when you imagine the beginning, do not picture a giant clock starting at 0 in a dark room. Picture something stranger. A universe so young that the room, the darkness, the clock, and the meaning of 0 were all part of the same unanswered question. And from that question, somehow, came every later tick. The pulses of stars, the decay of particles, the orbit of planets, the beat of your heart, and this quiet moment in which the universe, through you, wonders how it ever began to count itself at all. Quantum gravity may remove time from the equation. The deepest equation of the universe may not contain a ticking clock at all, and that may be the clearest sign that time is not what it seems. You live in a world where time feels impossible to remove. Every action seems soaked in it. A door opens after your hand touches it. A star shines because nuclear reactions continue in its core. A body grows older because cells divide, repair, fail, and change. Even thought itself feels like a procession. One word after another, one image after another, one memory rising and sinking into the next. So when physicists say that quantum gravity may remove time from the equation, it sounds almost like removing oxygen from breath. How could anything happen without time? How could the universe have a beginning, a history, or a future if the most fundamental description does not include a flowing clock? But this strange possibility appears because our two best theories treat time in radically different ways. In quantum mechanics, time is usually used as a background parameter, something outside the system that helps describe how a quantum state changes. The clock is assumed. The laboratory has time. The experiment begins, evolves, and ends. But general relativity, Einstein's theory of gravity, does something more radical. It makes time part of the physical universe itself. Time is woven together with space into space-time, and space-time can bend, stretch, curve, and respond to matter and energy. A clock is not outside gravity. It is inside the gravitational field. Its ticking depends on where it is, how it moves, and what kind of space-time path it follows. This creates a deep conflict when physicists try to build quantum gravity, a theory where space-time itself must obey quantum rules. If time is part of space-time, and space-time is what you are trying to quantize, then you cannot simply place time outside the theory as a fixed background. That would be like trying to describe the ocean, while secretly assuming a rigid, invisible floor beneath every wave. Quantum gravity asks for something harder. A description in which the stage itself is no longer fixed. Space and time are not passive scenery. They become part of the quantum system. And once that happens, the familiar clock variable can disappear from the most fundamental equation. In canonical approaches to quantum gravity, including the famous Wheeler-DeWitt equation, the universe is described by a condition it must satisfy rather than by a simple rule saying, here is how it changes from one moment to the next. The result is often called the problem of time. The equation seems frozen, not because the universe is literally dead, but because the usual external time against which change is measured is gone. If you are describing the entire universe, there is no outside observer with a stopwatch. There is no larger arena beyond reality where the universe sits and evolves. The universe contains the clocks, the observers, The fields, the geometry, the matter, the light, the measuring rods, and the memories. Nothing is left outside to say what time it is. So the theory may not ask, what does the universe do at the next second? It may ask, which complete configurations of geometry and matter are physically allowed? That change sounds small, but it is enormous. It replaces a moving picture with something closer to a whole structure, a set of possible shapes of reality that do not come labeled with one universal now. This does not mean time is unreal in the simple sense. It means time may be emergent, approximate, or relational, a feature that appears when parts of the universe are compared with other parts. When some physical degrees of freedom behave like clocks, when large-scale space-time becomes smooth enough for ordinary evolution to make sense. At human scale, time is not optional. Clocks work, planets orbit, signals arrive in order, your body ages. But at the Planck scale, where quantum gravity is expected to become important, the smooth space-time of relativity may no longer exist as a continuous fabric. The neat distinction between space and time may break into something more primitive. Some approaches suggest that geometry could be built from discrete quantum structures. Others treat space-time as something that emerges from deeper information, entanglement, or causal relations. None of these ideas is a complete final answer yet, and honest science must say that. Quantum gravity is still unfinished, but the repeated warning from many directions is profound. Time may not belong at the foundation in the way ordinary experience makes us believe. It may be like temperature, pressure, or the surface of water. Real and measurable at one level, but not a basic ingredient in the deepest microscopic description. A wave on the sea is real, but the ocean is not made of waves as fundamental objects. It is made of molecules whose collective behavior creates waves. In the same way, the flow of time may be real for beings inside the universe, while not appearing as a fundamental flowing parameter in the deepest theory. What makes this especially strange is that change itself may need to be redefined. Normally, change means something is different now than it was before. But if there is no fundamental external before, then physics must describe change through correlations. When one part of the universe has one condition, another part has another condition. When a physical clock reads one value, the rest of the world appears in a corresponding state. Time then becomes internal bookkeeping, not an outside river. You do not ask how the whole universe changes relative to a clock beyond it. You ask how the contents of the universe are related to one another. This is why quantum gravity can feel so difficult to imagine. It does not merely add new particles or stronger forces. It challenges the grammar of becoming. It asks whether the flow you feel is a large-scale habit of reality, born only after space-time has become classical enough, matter has become stable enough, and records have become durable enough. Near black holes, or near the beginning of the universe, where gravity and quantum uncertainty both matter intensely, that habit may break down. The smooth clock of ordinary space-time may no longer be reliable, and if the universe began in a state where classical space-time had not yet emerged, then asking what happened before may not be a normal question. Before may belong to a later layer of description. This is not an escape from science. It is a demand for more careful science. It means some questions that sound simple in human language may not survive unchanged at the deepest level. What was the universe doing before time? Maybe like asking what is north of the North Pole. The words make sense individually, but the structure they assume may not apply. And still, from this possible timeless foundation, your world appears. Mornings, seasons, aging, music, grief, memory, waiting, hope. That is the wonder. A theory may remove time from the fundamental equation, yet somehow time returns in the world you inhabit. It returns through clocks made of atoms, through the expansion of space, through entropy, through records, through the relationships between physical systems, through the way conscious creatures arrange experience into a life. The absence of fundamental time does not make your moments empty. It makes them emergent, delicate, dependent on deeper order. A rainbow is not less beautiful because it is not painted onto the sky as a solid object. It is beautiful because it appears when light, water, and perspective meet. Time may be similar. It may appear when geometry, matter, information, and observation come together in the right way. So when you hear that quantum gravity may remove time from the equation, do not imagine the universe stopping. Imagine the opposite. A reality so deep that motion itself is not the starting point, but something that arises from a more silent structure. Imagine that beneath every clock there may be no master clock, beneath every sequence, no universal sequence, beneath every now, no cosmic spotlight sweeping across existence. And yet here you are, moving, remembering, aging, listening. Perhaps the deepest theory will not tell us that time was an illusion, but that time was never a simple container. It was the way the universe learned to describe itself from within, the way a timeless foundation became a world of change, the way stillness at the root somehow opened into the fragile miracle of a passing moment. The flow of time may be something we add later. The flow of time may be the most convincing story your mind ever tells you. And the most difficult part is that the story works so well, you mistake it for the universe itself. You do not merely notice events, you feel them moving. A second seems to arrive, brighten for an instant, and fall away. A sound begins, becomes present, and disappears into memory. A face changes slowly across years, and only later do you realize the change had been happening all along. This feeling of flow is so intimate that it seems more certain than any equation, more obvious than any theory, more real than the chair beneath you. But modern physics asks a careful and unsettling question. Does time itself truly flow, or do we add the sense of flow after the deeper structure of events is already there? In many physical theories, time is used to order events, measure durations, compare processes, and describe change. But the equations usually do not contain a special moving spotlight called the present. They do not say that one moment is alive while all others are dead. They describe relations between states, events, fields, clocks, and measurements. They can tell you how one condition connects with another, how a system evolves, how fast a process occurs, how signals are ordered. But they do not usually explain why time feels like it is pouring through your awareness. That feeling may be something built at a higher level by brains, bodies, records, memory, and attention. This does not mean time is unreal. It means the flow of time may not be the same thing as time itself. A road can be real even if the feeling of travel comes from moving along it. A melody can be written on a page even before someone plays it. But the feeling of music unfolding appears only when a listener experiences the notes in sequence. In a similar way, the universe may contain events arranged in temporal order, while the sensation of a flowing present may be something living systems construct as they pass through, process, and remember those events. Relativity already makes the idea of a universal flowing now difficult. Observers moving differently can disagree about which distant events are simultaneous, and physics does not choose one observer's present as the true present of the cosmos. The universe does not seem to carry one grand cosmic cursor sliding across all galaxies at once. Instead, each observer has a path through space-time, a local chain of experiences, a personal ordering of nearby events. Your now is real to you, but it is not a universal blade-cutting existence into past and future everywhere. This alone weakens the simple picture of time as a single river flowing identically for all things. But the deeper mystery is not only in relativity, it is in consciousness. Your brain does not receive reality as a pure instant. It collects signals from the eyes, ears, skin, muscles, balance system, and inner body, then binds them into a usable moment. Some signals arrive faster than others. Some are predicted before they are fully processed. Some are delayed, smoothed, corrected, and woven together so the world feels continuous. The present you feel is not a raw slice of the universe. It is a carefully edited window, wide enough for action, narrow enough for coherence. Your mind builds a moving experience from fragments that are not perfectly simultaneous. And once memory enters, the flow becomes even more convincing. You remember what just happened. You anticipate what may happen next. Your body carries traces of previous moments, and your nervous system leans forward into possible futures. The feeling of flow may arise from this constant comparison. Fresh perception becoming memory, expectation becoming action, action becoming record. The present feels like it moves, because the brain is always updating its model of the world. It does not simply sit inside time like a stone in a stream. It actively manufactures a sense of passage by changing its own internal state. This is why the flow of time can stretch, shrink, blur, and fracture in human experience. Fear can make a moment feel wider. Boredom can make minutes feel heavy. Deep attention can make hours disappear. Sleep can erase the sense of passage almost completely, then return you to waking life with only a strange gap behind you. If time's flow were simply an external substance moving at one felt speed, your experience would not vary so dramatically. The variation suggests that the felt flow is partly an interpretation, a biological interface, a way the brain turns change into a livable story. Physics adds another layer by showing that the world can be described without giving the present a privileged glow. Some views of space-time suggest a block picture, where past, present, and future are not created one after another in a cosmic performance, but are parts of a larger four-dimensional structure. This does not mean your future choices feel known to you, and it does not remove the practical reality of decision, uncertainty, or causation in daily life. It means the universe may not be becoming in the same way your awareness feels itself becoming. The passage may belong more to your path through the structure than to the structure as a whole. That idea can feel cold at first, almost like it steals something sacred from the moment. But it can also be freeing. If the flow is something added later, then your experience of time is not a passive copy of the universe. It is an active achievement. Your mind takes a reality of events and relations and turns it into a journey. It gives direction to memory. It gives urgency to care. It turns physical change into biography. Without this added flow, there might be order, duration, and structure, but not the felt drama of a life moving through them. The flow may be the form time takes when reality is processed by a creature that remembers, predicts, fears, hopes, and loves. And this helps explain why the idea is so difficult to accept. You do not experience yourself as a full timeline. You experience yourself as a traveler. You feel that you are always arriving at the next moment, always losing the last one, always balancing on the edge between what can no longer be changed and what has not yet happened. This is the human shape of time. It may not be written into the deepest level of physics, but it is written into the structure of your awareness. A physicist may describe time as a coordinate, a parameter, a relation, or an emergent feature of deeper laws. But you live time as waiting, aging, remembering, healing, regretting, choosing. Both can be true at different levels. The mistake is to demand that the universe must feel from the outside the way you feel from the inside. A map does not contain the exhaustion of the walk. A musical score does not contain the tremble of hearing the song at night. A physical description of time may not contain the ache of passage, because passage may be what appears when a mind inhabits the description from within. So when we say the flow of time may be something we add later, we are not saying your life is fake, or that moments do not matter, or that the future is meaningless. We are saying that the felt river may be built from deeper ingredients: change, memory, prediction, entropy, attention, embodiment, and the local path of a conscious system through the world. The universe may provide the order of events, but you provide the feeling of moving through them, and perhaps that is not a reduction of meaning, but a deepening of it. The flow of time may be one of reality's most intimate collaborations with consciousness. The world changes. Your mind turns change into passage. The world leaves traces. Your memory turns traces into past. The world offers uncertainty. Your imagination turns uncertainty into future. Between them, the present appears, not as a universal spotlight, but as a fragile living interface. And maybe this is the quiet conclusion hidden inside all these mysteries of quantum time. Time may not be a river already flowing before anything exists to feel it. It may be what a universe of events becomes when part of it wakes up, remembers one side, anticipates the other, and calls the trembling bridge between them a life.